Good morning, Astronomy 1010. Today we are doing homework number 5, lecture number 7, and lab number 6, spectroscopy. That's our plan for the day. And our homework number 5 should be problems from chapter 5, 44, 53, 54, 55, and 57. I think that's correct. Couple words about the exam. I haven't gotten to grade them yet, but they should automatically be graded. Were you guys able to see your exam scores through Blackboard? Not yet? Okay. I'm going to need a day just to kind of wrap all that up and grade it up. But what I'll do is I'm going to try to give you an understanding of how your midterm grade works. And let me take you guys over to the office hour room. Just a second here. Looks like we can see the board okay, right? Okay. Here's what I'm thinking about your grades. I need to actually allow you guys to see your exam scores, but I haven't figured out how to do that yet because you guys were the first time I've ever given an exam through Blackboard using this format. So I'm going to have to kind of look into how to report and show the scores. But here's the basic gist of how this is going to work. Your exam score was out of 92 points. And your exam counts for both midterm and final because we decided that we only have time for one test if we want to learn about the moons of Jupiter this semester. So your score is some number out of 92 points. And when you divide it by 92 points, you'll get a percentage, right? So let's say, for instance, you get a 46. If you get 46 out of 92, that would be a 50% on your test, which doesn't sound that good to you, but it's not as bad of a deal as you might think. Because most of us are doing our homeworks in our labs and making sure that we keep up with it. So let's say your homework percentage, I think we'll have maybe 9 or 10 homeworks. And so you might have 250 out of 250 points. That's 100%. That's if you do all your homeworks with me. And if you turn in all your labs, you might get 100 out of 100 points if there's 10 labs, and that's 100%. And what I'm going to do for your final grade is I'm going to average these 25, 25, 25, 25%. And that would be 0.5 plus 0.5 plus 1 plus 1 is 3 divided by 4. So your total average for the class is a 75%. And this is just hypothetically speaking that if you got a 50% on the exam, just so you can understand how my calculation works. After that, I then apply the scale to the entire course. And the scale for my course goes in 5-point increments with 65% pegged to B minus. So an A would be anything over 85%. A minus is anything over 80%. B plus is 75% and above. B is 70%. B minus is 65%. C plus, anything over 60. Since there's no C minus, I drop C all the way down to 50%. And then D plus is 45%. Anything under 40% is an F, okay? So that's sort of the scale for the class. You can see that this hypothetical student got a 50% on their exam, which isn't so hot, but as long as they stick with me, do their homeworks and labs, they end up with a B+ for the class. So it's a very generous curve for the course, which guarantees that if you want to do well, you just have to kind of show up and you have to do your homework with me and you do your labs with me, which I don't think is asking too much. All right, do you guys have any questions about that? Okay. So like I said, it'll be more interesting to know what you actually get. And the moral of the story is just keep up with your homeworks in your labs so that I can give you a good grade a couple weeks from now at the end of the summer session, okay? All right, why don't we get into our homework for today? We're going to do homework number 5. Let me share that screen one more time. This is the guy we're going for here. Homework number 5, 44, 53, 54, 55, and 57. And why don't you guys call up those questions on your screens if you don't mind. This is homework. Chapter 5, 44, 53. 54, 55, 57. Okay. Megan, why don't you read us the first one if you don't mind?
Okay, 44. Atomic terminology, practice 2. A, what are the atomic number and atomic mass number of a fluorine atom with 9 protons and 10 neutrons?
Okay, hold on
If
a
we
second.
could add,
Let me catch up to you. We want the atomic number and we want the mass number. It's fluorine, right? Fluoride is a chemical.
Fluorine, yeah, my bad.
That's okay. So fluorine. And what were the details of the fluorine atom?
So it had 9 protons and 10 neutrons.
Okay, keep going.
If we could add a proton to this fluorine nucleus, would the result still be fluorine? What if we added a neutron to the fluorine nucleus? Explain.
Okay. So we have 4 little mini questions that we want to address here. Let's start with the atomic number. That's what I called A. Do you guys remember what that is? If you don't, you'll have to look it up in your notes.
Is it 9?
Yeah. Why is it 9? So I asked what the definition was. You instead told me the answer, which is fine, but maybe so that everyone's on the same page, we should remind ourselves why it's 9. Okay, guys, you're about 1 step away from getting the pre-recorded lecture here.
Number of protons.
The number of protons. Thank you. Okay. How about the mass number?
The mass number is the number of nucleons or the number of protons and neutrons. So would it be 19?
That's right. I guess I'll write some units up here just for fun. Although you're not supposed to need to, but. Nice use of the term nucleon. I approve of that. If we add a proton, Andrew, Adrian, Nick,
If you
someone-
add a proton, it becomes a different element.
do you know which one? What element has atomic number 10?
I don't remember off the top of my head.
Neon. It's a noble gas. If we add a proton, the element changes to neon. If we add a neutron,
There's no change in what element it is, but the mass number goes up.
yes, it's the same element, but a different isotope. If we add a neutron, the element remains fluorine, but a different, here's the key word, isotope, which would be called fluorine 20. And I believe, at least this is how they used to do it. They put the isotope number there. Sometimes they'll put -20. I see a chat here. Nick, mic and video are not working for some reason. You know what's funny? Nick, you have a black screen. Normally when someone isn't sharing video, it looks like this, but your screen is just black. So that's okay, Nick, that you're still here with us. We know that. But I wonder, I thought at first maybe you had a piece of tape over your camera, but maybe it's just wigging out on you. Let's just check how the pros write fluorine 20. Let's see what happens if we type that in there. Yeah. So you can see there are many known isotopes of fluorine, from fluorine 14 to fluorine 31. And as I remembered, they do put the mass number just up and to the left. Here's fluorine 20. Interesting. Many, many different isotopes. It's a whole world of chemistry out there, my friends, and it's interesting and worth learning about. Okay, gotcha, Nick. All right, let's see here. Megan, that concludes question A, does it not? Okay. So, Olivia, did you have time to get all that?
Yeah, I'll just take a picture of it if you don't mind, so I can just go back to it, and then I can just continue.
That's fine. Why don't
Okay.
you do that? That's just part A that you've missed.
Okay, perfect. Thank you.
All right. All right, I'm erasing. Does anyone have an issue with that? All right, here I go. Actually, okay. Megan, hit us with part B.
Sure. The most common isotope of gold has atomic number 79 and atomic mass number 197.
Wait. Atomic number
79.
and mass number 197.
Yes.
By the way, the symbol for gold, I believe, is AU, right?
Yes.
All right.
That I remember. How many protons and neutrons does the gold nucleus contain?
All right, that should be easy based on what we just did. What's our number of protons?
There's also more to the question. Do you want me to?
Let's do it one step at a time.
Okay, cool. It's 79.
Yeah. Okay. How about the number of neutrons?
118.
Yeah. So it's 197 minus 79. It's 118. Okay, what was the rest of the question?
Okay. If the isotope is electrically neutral, how many electrons does it have? And if it is triply ionized, how many electrons does it have?
Okay. Andrew, are you with us? I see a big light there. I can see your haircut. How many electrons should it have if it's neutral?
Hello.
Hi.
There we go. Should be 79.
Indeed. 79 electrons if neutral. How about if it's triply ionized, Andrew?
Would it be? Would you like times that by 3?
Not times it by 3. To ionize is to remove electrons from the atom. Did I spell triply right? Is there an EY? I don't know.
It's spelled right.
Oh, that's good. Do you see what I'm saying, Andrew?
So would you
I'm
just take?
I'm trying to gauge how much chemistry you guys know. So triply ionizing is to remove an electron. So if it's triply ionized, how many do you have?
You would take 3 away.
Sounds good. So leaving
That
us.
was 76.
Good. All right. Thank you. That's all of part B. Megan?
Yeah. Are you ready for part C?
Almost. I'm just going to hide the non-video participants so I can focus on the people's faces that I can see. Okay, that's better. Yes, I'm ready for part C after I erase. All right, hit us.
Part C is uranium has atomic number 92. Its most common isotope is 238U or 238 uranium. But the form used in nuclear bombs and nuclear power plants is 235U.
So these are 2 different isotopes of uranium.
Yes.
This is legendarily the one that creates yellow cake, the radioactive material used in nuclear weapons and in power plants. Okay.
How many neutrons are in each of these 2 isotopes of uranium?
Okay. Olivia, how do we do this? How do I determine the number of neutrons that each of these isotopes has? You're muted.
Sorry about that. So we're looking for the neutrons.
Correct. This is the atomic number for both for uranium,
Okay.
and they have different mass numbers.
Would you subtract 92 from both
Correct.
of them?
Right. So for uranium-238, we would have 238 minus 92. You can use your Casio for that if you want. We're still talking, right?
Yeah, 146.
Okay. And then how about for uranium-235?
That'd be 143.
At some point I'm going to teach you guys about nuclear activity because it's important in the sun and in the planets. And it's a cool thing to learn about. Which makes me, hold on a sec. I have something to share with you. If you can just give me 1 second here. I have it buried behind my desk because it's not exactly wholesome to spend time being exposed to it. But a friend of mine, when I lived in Tucson, Arizona, went out to this really weird swap meet in the desert where you can buy just about anything on planet Earth, legal or not. And he gave me a birthday present, my very own rock of uranium. And this here is a mixture of U-235 and U-238. You can see the yellowish appearance on the rock. This rock is called carnotite. It's highly radioactive, which is why I have it here in this lead box. Still emits a few gamma rays and beta rays outside of the box, which is not good, but that's why we keep it buried behind the desk where none of my guests can be exposed or minimize their exposure, you know. Sometimes I like to sort of irradiate my students with this. When they've been good students, they get irradiated. But I guess since you guys are far away, I can't quite do that to you this semester. I'll just have to irradiate myself. All right. All this radioactivity is making me a little hungry here. I mean, thirsty for coffee and caffeine. So before we read the next problem, why don't you guys take a peek at it? I'm just going to grab a cup of Joe, and then we'll be on to the next problem. All right, thank you, everyone. I had made a big pot of coffee, but it was just sitting there torturing me. So let's read the next problem, which is number 53. Adrienne, are you down to do that for me? Oh, bug in the house. Get out of here. Let her rip.
Electric bill.
Okay.
Your electric utility bill probably shows your energy use for the month in units of kilowatt hours. A kilowatt hour is defined as the energy used in 1 hour at a rate of 1 kilowatt, 1,000 watts. That is, 1 kilowatt hour is 1 kilowatt in 1 hour. Use this fact to convert 1 kilowatt hour into joules. If your bill says you use 900 kilowatt hours, how much energy did you use in joules?
Okay, I want to point out, because people sometimes miss this, that there are two problems in this problem. The first part of the problem wants us to convert 1 kilowatt hour into joules using our minds and math. And then the second part wants us to convert 900 kilowatt hours into joules. I'd like to point out to the new student that these are kilowatt hours. That's a kilowatt times an hour. It is not kilowatts per hour. Per means division, okay? How could I do such a thing? How could I convert? Oh, actually, did we actually talk about what watts are? I don't think we actually got there, did we, in our lecture? All right, so the crash course. Watts are a measure of power. Power is energy flow. Power is defined as energy per unit time. It's how much energy flows through a system. It could be a circuit, or it could be your body. It could be America. It could be anything. It could be a star. Energy is measured in joules. Time is measured in seconds. And we define joules per second as watts, okay? That's what a watt is. So in other words, 1 watt is equal to 1 joule per second. So we're going to use this and this to convert 1 kilowatt hour into joules. The technique that we're going to use, wait for it, dimensional analysis, okay? So let's start with our 1 kilowatt hour. And let's multiply by a division bar. What do you guys think we should do next? I'm going to write this up here so 1 watt is 1 joule per second. So we need that. We need that. How should we proceed?
Convert kilowatt hours to watt.
Well, Adrian, we cannot convert kilowatt hours to watts because kilowatt hours are an energy and watts are a power. But you do have the right idea, you're just saying it wrong. Adrian, we can treat the kilowatts and the hours as separate units. They are being multiplied, but that does not mean we can't deal with one at a time. So do you want to rephrase that for me?
Convert the kilowatts to watts.
Now you're talking business. So we'll do kilowatts on bottom and watts on the top. What's my conversion factor?
1,000 watts to a kilowatt.
Good. And once we cancel out kilowatts, what are our units currently in the problem here? What units do we have?
Watts and hours.
Watt hours. Do you follow me? Watts times hours. Watt hours. Let me just write that a little nicer. All right, now what?
Convert hours to seconds.
Okay. Hours go to the bottom. Do you know the numbers of seconds in an hour, or should we go to minutes first?
Like 3,600.
Fine. I'll let you do that then. There are 3,600 seconds in 1 hour. Adrian, what units do we have now?
Watts and seconds.
Right, but instead of saying watts and seconds, like cats and dogs, let's say watt seconds, or at worst, watts times seconds. Okay? Watt seconds. Now what? So far, you've been right on point. What should I do next, Adrian?
Watts to joules.
You can't convert watts to joules because joule is an energy and watts are a power. But you can convert watts to...
Joules per second.
Okay, fine. So tell me what units to put up here.
Joules per second on top and watts on the bottom.
And the conversion is 1 to 1, right? Watts, seconds. What units do I currently have? Just showing you my copy because I don't know what else to do. What units do I have right now? Well, I thought that answer was obvious, but I guess it's not, huh?
Joules.
Okay, fine. I just needed to make sure that you all understood that. All right, so how many joules are there then? Let's see, we don't need a calculator for this, do we? 3,600, 1, 2, 3 more zeros. What do I got?
So 360,000.
False. Try
36.
again. Megan?
Yes. 36. Is it 36,000?
No. You already have 3,600. You're going to multiply it by 1,000. Megan, squish them all together in your mind. You've got 1, 2, 3 zeros, 4, 5, and then the 6. So try one more time.
Would it be like 3 million?
3.6 million, right?
3 million, yeah.
So how do I do that in scientific notation? 3.6.
3.6 times 10 to the 6th joules.
Very good. 1 kilowatt hour is 3.6 million joules. Now, in answering the first question, we've actually created a new conversion factor. We know how many joules are in 1 kilowatt hour. I wonder if I have a national grid bill here. I'm sure I do because I hardly ever pay it. You are scheduled for termination. No, I'm just kidding. Actually, I'm not entirely kidding. Oh, this is for gas. It's measured in British thermal units. Ooh, we have not received payment. I was hoping to. They're not very happy with me. Anyways, I was hoping to find an electric bill where it shows you the number of kilowatt hours you used, but each letter I open is a little more frightening than the last one, so I'm not going to do that anymore. Okay, so what should I do next if I want to convert 900 kilowatt hours to joules? What now?
Do you times the 900 kilowatt hour by the 3.6 times 10 to the 6th power?
Exactly, Yimmercy. I wanted you guys to recognize that we don't have to redo this all over again because we have a new conversion factor from kilowatt hours to joules. But my only complaint, Yimmercy, is that I'd like to make a dimensional analysis like. So what we'll do is we'll start with our 900 kilowatt hours. We're basically going to do exactly what you said, Yimmercy, but we're going to do it in the form of dimensional analysis. We are now going to convert from kilowatt hours into joules. So now we're treating the unit as a single item, right? Which is different than how we did it before. And Yimmercy, where should the 900 go? Well, you already told me. Sorry. You said to multiply 900 by this number. So it's 3.6 times 10 to the 6 joules is 1 kilowatt hour. Okay, guys, punch that up for me and tell me what you get. This one you do want to use a calculator for.
Is it 3.2 times 10 to the 9th power?
Yep, 3.2 billion joules. And that concludes question 53. It's a little out of focus up there, huh? All right, I'm going to erase here. Chapter 5, 54. Andrew, you down to read that one? Because you're the next little face in my squares here.
I'm just loading up the file right now.
Okay.
Okay, 54.
What's the title of this one?
Radio station.
Okay, before we begin, this question is also just a tiny bit ahead of where we are in our lecture. So let's first draw a little picture of what's going on here. So let's draw a little radio tower, okay? Before you read it, Andrew, we're going to draw this. So let's draw a radio tower with a blinking light. And let's have a radio wave coming out of it. A radio wave is a form of light that's very long wavelength. It's a type of light that your eyes can't see. And when we draw waves of light, electromagnetic waves, we tend to sort of make a little squiggle that looks like this. This is what a wave looks like. Waves have some different properties that we're going to study in this problem. The distance from crest to crest in your wave, that's called the wavelength. And the symbol for wavelength is the Greek letter lambda. It looks like an X that's missing an arm, okay? Wavelength is usually measured in meters, but it can also be measured in nanometers. Another property that light has, and you should probably put this down on your paper because you're kind of learning it as you do it here. Curve EF is going to represent the frequency of the wave. The frequency is like the number of cycles per second that comes by. So frequency is measured in a unit called hertz, where a hertz is, it's funny, you actually write it as 1/seconds, but the concept is cycles per second. Cycles isn't a real unit. Hey, I want to see if I can bring the focus up here by opening my Logitech app for my camera. Logitech capture, okay. I've got this background app that will help me adjust focus, so just give me a second here. Okay. I'm just going to adjust the focus here. Oops. Install later. Wow, this thing is irritating. All right, let's try that again. Autofocus is off. I'm just trying to figure out where the best focus is here. Not that. Okay, maybe it's just that my laptop is at an angle or something. All right. I'll minimize that in the background. The last thing that a wave of light has is an energy. And the energy is measured in units of joules. Okay, now, before Andrew, the thing I wanted to talk about before we got into it is this, this problem requires us to use one of three formulas that we're going to be studying in this class. There is the speed of light is the wavelength times the frequency. We're going to call that equation 1. The second equation is that the energy of a photon is Planck's constant times frequency. Now, I think what I'm going to do here is we have a few constants of nature. I'm going to put them in purple so that you can see that the purple numbers are fixed numbers that don't change. All right? And there's a third formula, equation 3, which says that the energy of a photon can also be expressed as Planck's constant times the speed of light divided by the wavelength. Now here I have to define what h and c are. C is the speed of light, 3 times 10 to the 8 meters per second. That's the speed of light in a vacuum. And h, something called Planck's constant, is 7 times 10 to the minus 34 joule seconds. The numbers that I have in purple here, I don't know if they look very purple on your screen, but they're purple on my page here. Those are constants of nature and they don't change. Okay, Andrew, I think I'm finally ready for you to read the problem.
Okay, it says, what is the wavelength of a radio photon from an AM radio station that broadcasts at 1120 kilohertz? What is its energy?
Okay, let's first recognize that kilohertz are a frequency. That's what they've given us here. We need to convert this and we need to find the wavelength and we need to find the energy. How do you guys want to begin? What do you guys think we should do?
solve for wavelength using Formula 1?
Exactly. All right. Do you have the chops to do that?
Perhaps. Okay, so first of all, you're going to want to have wavelength where C is. So,
Can I caution you here?
yes.
A lot of times people want to get wavelength on the left-hand side. So like the way you said it was, I want to see where wavelength where C is. But I
Yeah.
would actually advise against that because what's less important is whether it's on the left or the right. And what's way more important, Megan, is whether it's on the top or the bottom. And right now, wavelength is on the top. So why don't you leave it on the right-hand side and get frequency over to the other side? What would it look like then?
So then it would be C over F, or C over frequency.
That's right. So you have C over frequency equals wavelength. And now because equations are symmetrical forward and backwards, if C over F is equal to wavelength, wavelength is equal to C over F, right? So it's much better to leave wavelength alone if it's on the top. Okay, now what are we going to do? Let's write our
All right.
formula.
Now you're going to put in the numerator 3 times 10 to the 8th meters per second.
Yep.
And in the denominator, you're going to put, would it be 1120 kilohertz?
Here's where I've got an issue with that. See, frequency wants to be expressed in hertz, which is 1 over seconds. The 1 over seconds will cancel with the per seconds here. But kilohertz is not the same thing as hertz, is it? So how do I deal with that?
Dimensional analysis, right?
Yes. Okay, so let's do a little mini game down here, as they say in Zelda. This will be a mini game, okay? So if I have 1120 kilohertz, we want to go from kilohertz to hertz. Megan, you're muted, so I don't know what's happening.
I need to pass if someone else could take.
You can't convert kilohertz.
Oh, is it 1,000?
Of course, anything that's kilo is 1,000.
My bad. All right, so it would be 1,000 on the numerator and then 1 on the bottom. Right,
yeah.
Denominator.
1 kilohertz would be 1,000 hertz. Okay, so what's my frequency then? Can you do that in your head?
Yeah, so that'd be 1.1. Would you keep the 2?
We might as well. It's there.
Okay. Times 10 to the 6th.
And that's hertz, right?
Yes.
But here's how I'm going to put it into the equation. When I put it into the equation, instead of writing hertz, I'm going to write the equivalent of 1 over seconds. So this becomes 1.12 million cycles per second. Sorry, things are getting a little squishy down here. Go ahead and punch that one up for me.
Um, 267 point.
Whoa. Let's not get carried away with precision here. You've got 3 sig figs at best.
Okay. 268 then.
Sure. What are the units?
Meters per second. Sorry.
No.
No, hertz. I'm sorry.
No.
I don't know.
Do your dimensional analysis here. Here. Let's draw in big letters what's going on with your units. On the top, you have meters per second. On the bottom, you have 1 over seconds. What does that turn into?
Meters.
That's right. Per seconds cancel with per seconds, leaving you with just meters, which is a wavelength. A wavelength is a length after all. All right, now we got to deal with the energy. Everyone getting this? Olivia, how do I deal with the energy?
Okay, so yeah, you'd use that formula for the energy, E equals H times F.
Now, H is over here, right?
Yep.
That's Planck's constant. So I have 7 times 10 to the negative 34. My units are joules times seconds for Planck's constant.
And then the frequency, would that, no. 120, no, sorry. 1,120 kilohertz down there.
How do I say that? That's not 1,000. What does 10 to the 6 mean?
Oh wait, I'm sorry, which one were you pointing at? Was it,
Yeah, which one was I pointing at? Where's the frequency?
okay, hang on.
The frequency wants to be in hertz.
Yep. So be, oh, I'm looking at, sorry, my screen was blocking that. It was 1.12 times 10 to the 6th hertz.
Right, but I'm going to write it as 1 over seconds.
Okay.
Anyways, you got it. So what do I do now? So now I punch them into my calculator.
Okay.
Sorry, I wanted to get that all on a single page, but I couldn't.
7.84 to the negative 28.
What are my units?
Would be joules.
Yeah. Box that up too. That way I know what your answer is. Okay, that problem's done. Olivia, stay with me. Maybe you can read the next one. This homework goes by pretty quick, actually.
All right, so let's see.
I'm going to erase here.
Yep. So we're on 55.
Yes.
Okay. Okay, 55. UV photon.
Okay.
What is the energy in joules of an ultraviolet photon with wavelength 120 nm?
That's nanometers.
Okay.
Let's define that off to the side here. 1 nanometer is a billionth of a meter. Billion is 10 to the 9, so billionth is 10 to the minus 9. That's an important conversion factor in today's class.
And then what is its frequency?
Okay, we're going to want the same formulas that I had you write down for your previous problem. So consult your equation sheet there, 1, 2, 3. How should we begin?
So the energy formula is E equals, is it H times F or hertz times frequency?
That would work if we knew the frequency, but here the frequency is unknown.
Okay, so time hertz times, did I write C? Yeah, C over wavelength.
Yeah, H stands for Planck's constant, not Hertz, but Planck's constant.
Oh, I'm sorry. Okay.
It's okay, you're just learning that. So we're going to use what I called equation 3.
Yep.
The energy is Planck's constant times the speed of light divided by wavelength. However, these formulas are MKS formulas, where M stands for meters. So our first job should be to convert the wavelength from nanometers into meters. So let's start there. Olivia, give me some units, top and bottom.
Okay. Nanometers to meters. So nanometers would go in the bottom, the denominator, and then the top would be meters.
Yep. And now give me some numbers.
So the top would be 1 times 10 to the negative 9.
Yep.
And then in the bottom would be 1.
Okay. Now, a simple way to do this, Olivia, is instead of punching it into your calculator, we're just going to do 120 times 1 is 120 times 10 to the minus 9 meters. I like to write it this way because in my head, I think of 10 to the minus 9 as the same thing as nano. Nano is a billionth, right? Now, if you punch into your calculator, you'll get 1.2 times 10 to the minus 7. But I don't think that's quite as catchy as 120 times 10 to the minus 9 meters. That's my personal preference. Okay, so now we can plug this all into our equation. So the energy will be Planck's constant, 7 times 10 to the negative 34. I'm going to put these in better color here. The units are joules times seconds times the speed of light, 3 times 10 to the 8 meters per second, all divided by 120 nano meters. Go ahead and punch them up in your calc-key.
.75 to the negative 18th.
Let's just make it 1.8 for fun.
Okay.
But you're supposed to say 1.8 times 10, Olivia.
Okay.
You gotta say the times 10.
Okay.
What are your units? Wait, is that right? Did anyone else get that? Yeah, you got that too, Megan?
C.
C as in the speed of light, or C as in yes? I'm just kidding. All right. I'm being a dork. What are the units, Olivia?
Joules.
Yeah. Meters cancel, seconds cancel. It's an energy after all, so it better be in joules. Okay. So we had to get the energy. We also have to get the frequency. Which equation do you want to use?
Would it be the E equals H times F, the energy?
We could definitely use that equation because now we have the energy. That's totally okay. But do you know how we derive the energy from the original given? Whenever I have the opportunity, I prefer to go from the original given to the new number because this has a bit of rounding in it and will introduce a tiny bit of rounding error. Honestly, for a test or something, it wouldn't really matter. So your method would have worked, but I'm going to suggest we do equation 1. Speed of light is wavelength times frequency.
Okay.
I'm erasing here.
Oh, hang on 1 sec. Sorry. Let me just.
Okay. Yeah.
Okay. You're good.
All caught up?
Yeah. Thank you.
Were you screenshotting? Is that what was up? Yeah.
I'll go back to it after.
Oh, are you sure?
Yeah, totally fine.
All right.
Good. Thank you.
So speed of light is wavelength times frequency. If I solve for frequency, what's that going to look like?
Would it be C over wavelength?
Yeah. C is 3 times 10 to the 8 meters per second. Wavelength is 120 nanometers. And when you're ready, punch them into your calculator and tell me what the frequency is.
(2.5 times 10 to the 15).
What are my units?
Seconds?
Careful.
Meters.
No.
No, meters cancels out.
It looks like seconds, but it's not seconds. Why? Something's wrong. Adrian, do you know?
Is it 1 over second?
Yeah, there's a big difference, Olivia. This isn't just seconds. This is seconds in a denominator. Per seconds are not the same thing as seconds. When it's on the bottom, it's different.
Okay, that makes sense.
Yep. A per second is the same thing as a hertz. So what this really is 2.5 times 10 to the 15 hertz. Let's write it both ways to demonstrate their equivalence. And that concludes question 55. One more to go, and then we get a nice juicy break before class. I'll just let everyone catch up there. Adrian, are you down to read us the final one? Is that cool? Awesome.
Yeah.
I'm erasing unless anyone has an objection. Oh, before you begin, Adrian, let me tell you guys what this problem is all about. Today, you're going to be learning a lot about light, and I think it's a pretty interesting lecture. I hope you will too. This is what's called the visible continuous spectrum. This is the different types of light that your eyes can perceive. And one color differs from another by a property called wavelength. In this problem, we're going to be dealing with a light bulb that's only emitting light at a wavelength of 600 nanometers, which you guys can see corresponds to the color orange, right? So in a way, this next problem is kind of like, if you ever go to Home Depot, you can get a party light bulb. They have a section in the light section, and oh, that's a real party bulb. That's cray cray. But sometimes you can get these like colored party bulbs. I guess this would be like a yellow party light or an orange party light. Anyway, oh, there we go. So this problem is basically about this. It's about an orange party bulb, okay? All right, So Adrian, take us out. I'll even draw the party ball here.
Okay, number 57, how many photons? Suppose that all the energy from a 100-watt light bulb came in the form of photons with a wavelength 600 nanometers. A, calculate the energy of a single photon with wavelength 600 nanometers. B, how many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb? And C, based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
All right, that's a lot, but we're going to take it one step at a time. Part A should actually be easy because part A is a regurgitation of what we did in the last two problems. What equation do I want to find the energy of one single photon of wavelength 600 nanometers? Look at your three equations I gave you earlier. Adrian, do you know which formula? I lost you. Your face is missing. Oh, there you are. No, there you are. Okay. Adrian, of the three formulas that I gave you in the two problems ago, which do you think would be best suited for this job?
I'm not entirely sure, I'm sorry. I'm
Okay.
a little foggy right now.
I
Not
guess
feeling very good.
Oh, does someone else want to guess? That's okay, Adrian. I'm a little foggy too. Megan, what are you thinking?
I'm also foggy, but I'm thinking like equation 3.
Yeah. Which is energy of a photon, Planck's constant times the speed of light over the wavelength. Sometimes it's easier to think when you're not the person that's on the spot. I get that. The reason why Megan said this is because we've been given a wavelength. This, by the way, is the power of the bulb. It's sometimes also known as the luminosity. So the luminosity is going to be coming into play in the next part of the problem. But for now, the wavelength of light determines the energy of one photon. So the only issue is we should convert 600 nanometers to meters. Do you remember the conversion, Adrian?
Um, 1 times 10 to the negative 9 meters.
Which basically gives us 600 times 10 to the minus 9 meters. That's the wavelength. Okay. So now we're ready to plug into our equation. The energy of the photon is Planck's constant, 7 times 10 to the minus 34. I'm going to use red instead of orange because it's a little clearer. Joules times seconds. Ooh, this is a bad red. Okay. Oops. That really went flying. Okay. Times the speed of light, meters per second, divided by 600 nanometers, or 600 billionths of a meter, I should say. Okay, guys, give me the energy. Punch them up nice and quick. I want to get a ham and cheese sandwich before class.
Would it be 3.5 times 10 to the negative 9 joules?
Yes. Good, box that up. That's the energy of one photon. Okay, Adrian, we're gonna need you to read B again because we already forgot.
How
Hold on,
many?
Adrian, I'm sorry. Did you have a chance to copy all this down? Because I want you to. You good with this?
Yeah.
Okay.
How many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
Okay, so what we're looking to find is the number. Photons are like little particles of light. They're little packets of light. And what we're looking for is the number of photons per second. And because you haven't studied light too much yet, there's no real formula for this. It's a conceptual idea. The way we want to do this is we want to start with the luminosity. Our bulb is emitting 100 watts. And you'll remember that 100 watts is the same thing as 100 joules per second. That's telling us the number of joules that are streaming out of the bulb each second. But each joule, each joule of energy contains a whole bunch of photons in it. And each individual photon is a tiny little bit of energy. In fact, if you think about it, what we really need to have happen to go from joules per second to photons per second is we need a conversion from joules to photons, where photons is a kind of dummy unit. And we already have that because we calculated that one orange photon has a single energy of 3.5 times 10 to the minus 19 joules. And that's a really tiny number. So if we know 100 joules come out of the bulb each second, dividing the 100 joules by the energy in one photon should cancel out joules and give us the number of photons per second. What is that number?
Three times 10 to the 20th.
And that's what units?
Photons per second.
Right, which is an incredible number of photons if you think about it. That's a very big number. Now I'm going to step us through part C because you guys haven't quite learned enough about light yet. Just going to let you guys catch up here. All right, I'm racing. In part C, the question goes something like this. Why can't I see one photon of light? Your first thought might be, well, if there's 3 times 10 to the 20 photons, that there's too many of them to see individual ones. But if you meditate on this answer for a few minutes, you'll realize that that answer doesn't make sense. Just because there's too many of a thing does not mean you can't see individual members. There are too many stars in the sky, but you can see individual stars. There are too many grains of sand on the beach. But if you hold up grains of sand close to your eye, you can see individual grains of sand. It's not that there are too many. Your next thought is that at 600 nanometers, the orange photons are too small. But you'll quickly realize that that also does not make sense. Yes, an orange photon at 600 nanometers is quite small. But it turns out that all orange light has a wavelength of 600 nanometers. And your eye is capable of detecting 600 nanometer photons. Otherwise, you would not be able to see the color orange. So since all orange light is at 600 nanometers, too small isn't the answer. Another common misconception is that maybe they're too fast. This is also incorrect. Because all light has the same speed of 3 times 10 to the 8 meters per second. If light was too fast to see, you wouldn't see any light. Eventually, you start to realize it's not about number, it's not about speed, it's not about size, but it's about a different quantity, energy. The energy of a single photon is basically 3.5 times 10 to the minus 19 joules. And that's an incredibly tiny amount of energy. Your eyeball has a minimum threshold of energy that it needs to create a stimulation. And the correct answer is there is not enough energy in a single photon for our eyes to detect it. Handwriting was bad there. And that's the answer to part C. Okay, class, it's 11:37. That gives us a good 20 minutes to break before class begins. Does that sound good? I'm gonna run downstairs and get a little ham sandwich to power me through today's lecture. So at 12 o'clock, we will resume if there are no other questions. And I'll see you guys then. Sound like a plan? All right, I like it. I'm gonna pause the recording. Don't let me forget. Hello, everyone. Just gonna give the board a little spritz here. So we're gonna pick up where we left off last time. We finished up atoms. Now it's time to do light. And there's a lot to talk about today. Ooh. Sorry, this board is filthy. Okay. All right. So we're going to talk about the macroscopic and the microscopic properties of light. We could begin with a slide or two. One of the first experiments ever done by Sir Isaac Newton was to take a prism. Let's see here. This is slide number 18. Oops. Cancel. And he sent a beam of white light through a triangular piece of glass, and he discovered that he could separate the white light into a component of colors. We call this a spectrum. Now, I like to do this demo in class, but I don't have a bright enough light source or a collimated enough light source, but I do have a small prism here. It's just a triangular piece of glass, nothing fancy about it. And if you pass white light through this prism, you can separate it into its colors. The order of the colors is always the same: red, orange, yellow, green, blue, which you can think of as a sky blue, indigo, which is kind of a dark blue, and then violet. And together, these colors make up what's called the visible continuous spectrum. Let's take some notes on that. Okay, so if you take a prism, which this is what Isaac Newton did. He did some of the first experiments in light. And you send a beam of white light into the prism. You can separate the colors into a rainbow. But from now on, we're going to call the rainbow the visible continuous spectrum. A spectrum is when you break light apart into its component colors. And sometimes the order of the colors makes a little mnemonic device. Red, orange, yellow, green. My color choices are somewhat limited here. Blue, indigo, and violet. It's an acronym known as Roy G. Biv. And the orders of the colors are always the same. People sometimes call it Roy G. Biv. And it turns out that color corresponds to a property of light called wavelength. Color is the psychological experience of something called wavelength. In our class, wavelength gets the symbol lambda. The wavelength of a wave, if a wave looks like a sine function or a cosine from your math class, waves are always, and there are different types of waves. There are transverse and longitudinal waves, but mathematically, a wave is usually some kind of a traveling displacement. The wavelength is defined as the distance of a repeating cycle of the wave. So here, in my transverse wave, the wavelength is the distance from crest to crest. So the wavelength is the length of one cycle of the wave. That's one way to say it. It can be measured in units of meters. It can be measured in units sometimes of nanometers, and in some instances, micrometers. And we're going to use NM for nanometers. When we describe micrometers, we use the Greek symbol mu. It looks like this, mu, M. Mu is like a U, but with an extra tail on it. Let's write down a couple of conversions that might be helpful here. 1 nanometer, as you know from your homework session today, is a billionth of a meter. 1 micrometer is a millionth of a meter. One of the reasons why nanometers are popular is because your first foray into studying light usually begins with studying visible light. And visible light can be nicely expressed in terms of nanometers. Violet has a wavelength of around 400 nanometers. Red has a wavelength of 700 nanometers. And this is about the extent of what your eyes are sensitive to. Now, it turns out that when you separate light into its component colors, whether or not you get red first or purple first depends upon the angle with which the white light hits the prism. You can turn the prism around and get violet to appear first. Historically, people like to describe the spectrum as Roy G. Biv, but I actually prefer to do it backwards and spell Vib G. Yor, because then your spectrum goes in order of increasing wavelength, which I like as an optical astronomer. So let's try this again. I need to erase these notes to reuse the board, so if everyone's caught up, I'm going to erase now. You all good? All right. So let's introduce again to you guys the visible continuous spectrum is sometimes called the visible regime, or sometimes people call it the optical regime. Astronomers call it optical because optics lenses usually deal with visible light. And in this case, we can rewrite the order in an increasing wavelength: violet, indigo blue, green. I like this. I think this is a little better. Yellow, orange, and red. Otherwise known as Vib G. Yor. Vib G. Yor is the way I like to do it. The wavelength of red, 700 nanometers. I want you to memorize these. The wavelength of violet, 400 nanometers. And green has a wavelength of 500 nanometers. So that's a good way to remember the visible spectrum. Here, wavelength is increasing to the right, which is why I like to put purple on the left-hand side. But let's learn a little bit more about this light, okay? Let me show you a more sophisticated model of light, one from a physics course. Light is what's sometimes known as an electromagnetic wave. Oops, sorry. Let me get the right slide here. I have a slightly jazzier description of light here, slide 25. Bear with me. I'm going to share my screen, and we're going to go to slide 25. By careful studies of the connection between light and electromagnetism, we have discovered that light is an electromagnetic wave. And here's a little model of how light works. It's got two parts to it. One part is an electric field, which is related to static charge coming from protons or electrons. The other component is a magnetic field. Magnetic fields are related to moving charges, moving protons and electrons. It turns out that electric fields and magnetic fields are both part of the same force, the force of electromagnetism. So we refer to light as an electromagnetic wave. I think I can shed some, pun intended, light onto this by having you guys take a look at one of these physics Java apps with me. See if I can show you guys something fun here. In the S drive, I have these physics Java apps, and one of them is a radiating charge. Okay, so bear with me here. Here you can see a proton, although I could have used an electron. And the proton is surrounded by an essence of charginess called the electric field. The electric field tells other charges how to interact with this proton. Now, the electric field is not light itself. It's a force field related to the charge of the proton. But if I take this charge and I give it a wiggle, I can create little ripples in the electric field. And these ripples are what light is. If I give it a sinusoidal oscillation, I can even adjust the frequency and change the wavelength here. So watch this. Here is a high frequency wave. I'm shaking a number of cycles per second quickly. And I can drop the frequency. And basically the waves that are coming out of this is what light is, all right? It's ripples in the electric field. Let's take notes on that. So light, I think I might have killed this marker here. You know what? Let's give this puppy a break. Let's get out a fresh one. So light is an electromagnetic wave. It has several properties. It's one part is the electric field. The electric field is associated with static charge. Static means my charges are not moving. An example of the electric field would be when you pull socks out of the dryer and you see the little crackle and the sparks. That's caused by the electric field. Saran wrap is basically a sheet of rubber with electrons sprayed onto it. Saran wrap uses an electric field. One part is the magnetic field. The magnetic field is associated with moving charges. It's hard to draw this unless you have good art skills. Usually what happens is you just draw the electric field and you represent it something like this. The magnetic field is always perpendicular to this one in and out of the plane of the board. So this is a ripple in the electric field, for instance. Light has a number of properties, and they're the same properties that all waves have. In fact, you can call them properties of waves. And there are many different properties that waves have, but some of the most important that we've discussed are wavelength, gets the symbol lambda, frequency, that gets a curvy F, and energy. E. Each of these things have different units. In the MKS system, the units are meters, hertz, which are cycles per second, and energy is measured in joules. Hey guys, can you just give me, can I pause for just 1 second here? Give me 1 minute, I'll be right back, sorry. Very sorry about that interruption. Okay, sorry about that. Let's get right back to it. Properties of waves. You already learned about these in your office hours today. Wavelength, frequency, and energy. These are some of the properties that all waves have. Example of waves could be the waves on a string, like when you pluck a guitar or drag a bow across a violin. Sound is a form of waves. They are compressional waves, not side-to-side transverse waves, as they call them. Ocean waves have a little bit of transverse and compressional components. Whether you're talking about sound, light, or waves on a guitar string, all of these waves have a wavelength, a frequency, and energy. They're part of the fundamental properties of waves. And today you're going to study some of the more exotic properties that waves have as well. Just to give you a heads up on where we're going, other properties that waves have in common that I would like to talk about in today's lecture. Waves have they undergo something called interference. Sometimes they call it superposition. Waves can add and subtract. So let's put that in parentheses underneath each other. Waves add and subtract. They create interference patterns. Waves can undergo something called diffraction. Diffraction is what I'd like to talk about today, later on today. Diffraction is a bending of waves when they pass through openings. Waves can undergo refraction, which is another type of bending. When I pass white light, or when Newton passes white light through a prism, and the light separates into its component wavelengths, let's go back a couple of slides here. This is a form of refraction where the purple light gets bent by a larger angle than the red light. This is how you separate colors from each other, and that's a bit of refraction. Sometimes they also call it dispersion. Dispersion means you're breaking apart colors. There are some other properties that waves have too that they reflect, they scatter off of objects. You know, when people want to learn about waves, sometimes they contrast waves with particles. And these little moon balls here would be an example of a particle. A particle is usually considered to be some BB or some self-contained unit. And when particles come in contact with each other, boink, they tend to kind of bounce off one another and they travel in their separate directions. Unless you're dealing with like silly putty or Play-Doh, you can't really take particle A and particle B and smush them together into a bigger particle. They kind of are separate packets. They don't want to be disturbed. And let's contrast this a little bit with a slide that I have of waves on a string, so that you can see what makes waves a little bit different than particles. Here's a picture of what we call interference, the interference of two waves. Slide 40. If I send a little pulse or a crest down along a string, and it bumps into a trough, a sort of negative pulse, at the moment when the two waves overlap one another, the waves will actually superimpose and interfere with each other. And the crest and the trough will cancel each other out to make a nothing. A moment later, the waves separate and carry on their merry way. On the other hand, if two crests are to bump into each other, you can make an even larger crest. This is what makes waves different than particles. Waves can interact and they can superimpose, and just like numbers on a number line, they can add. And this leads to some kind of cool effects, right? Like if you throw pebbles into a pond and you make spherical waves, here the bright fringe could be considered the crest of the wave and the dark fringe could be considered the trough. You'll notice that there are places where the crests and the troughs are meeting up with each other, and they create what's called a destructive interference pattern. This pattern here is sometimes called an interference pattern. If I were to use my annotation tool, these are zones of constructive interference where the waves add. These are zones of destructive interference where the waves subtract. And not only does this happen with water waves, hell, it even happens with sound waves. And Greeks designed their amphitheaters so that two thespians standing here and having a conversation on a stage could amplify each other's voices constructively, and members of the audience sitting in these zones of constructive interference would be able to hear the characters even if their voices went close to a whisper. Meanwhile, the aisles, you'll see the aisles are designed so that they lie along destructive interference nodes. And once you step out into the aisle, it becomes quiet because the waves cancel each other out. So this happens in theater design as well as light waves and such. In any case, we're here to talk about light. And this was your first description of light that I showed you. Let me show you a slightly more advanced one. Here's a propagating wave where the green arrows represent the electric field and the blue arrows represent the magnetic field. This is a much more sophisticated picture of light than the one you saw before. In the previous thing, we kind of represent the electric field as a blue wiggle, and we represent the magnetic field as a red wiggle. But in fact, in higher order classes, you will discover that they are something called vector fields. Every point in space has a direction and a magnitude. That's probably a little over your pay grade, but we can still learn some things by studying this traveling wave. You'll notice that the wave is traveling through space. And what I would like to do is take a look at its wavelength, first of all. So I'm freezing it for a moment and I'm grabbing its annotation tool. This is the wavelength of the wave. It's the distance from crest to crest or trough to trough, however you want to do it. We can also measure it here, if we want to, from node to second node. The wave also has a frequency. So let's see how we can represent the frequency. The frequency is the number of cycles per second that your wave exhibits. So what I'm going to do is I'm going to put a red arrow. Let's see if this will work here. Let me clear that. I'm going to put the red arrow here. What we're going to do is we're going to count the number of cycles per second by watching how many waves go past. We'll start at the crest or at the trough or something. Let's see if I can start this up again. Okay. So let's start when this trough goes by. 1001, 1002, 1003, 1004. Okay. So basically what we saw there is we saw one wave traveling past every 4 seconds. And let's take a look at the units of frequency together, okay? So in that last experiment that I just did, we took a look at a wave that completed one cycle every 4 seconds. I know it wasn't exactly 4 seconds, but it was close, okay? And cycle is kind of a dummy unit. It doesn't really, a second is a measurable conceptual quantity in physics, where a cycle is like an idea. It's like a repeating doodad or something. So we would say that the frequency of this wave, one cycle every 4 seconds, is 1/4 per seconds. And because per seconds sounds weird, we can also represent it as 0.25 hertz, where in the MKS system, as I mentioned already, 1 hertz is a per second. Even though it looks like 1/seconds, you should probably think about it in your brain as cycles per second. That's more helpful. So the frequency tells you the number of cycles per second. And these properties of waves are, of course, related to each other by the formulae, which we took a look at earlier in our lecture. And the first formula was the speed of light is wavelength times frequency. By the way, this isn't just true for light waves. This is true for sound waves, too. Here, C is a constant of nature, 3 times 10 to the 8 meters per second is the speed that all light travels at when it is in the vacuum of space. It turns out light travels a bit slower through air and a bit slower still through glass and water, but we'll get into that later. We can also measure the energy of one photon. Actually, I probably should talk about what a photon is. And those formulas are E is Planck's constant times frequency, or the energy of a photon is Planck's constant times the speed of light divided by wavelength. I sometimes call this one equation 2, and I call this one equation 3, just because they don't really have easily sayable names.
All right, I have a question.
Yeah, sure.
So the H is a what constant?
Yeah, let's talk about that. This is some stuff you may not have heard about before. H is something called Planck's constant. And it's named after the German physicist Max Planck. Max Planck in the early 1900s discovered properties of atoms and light that were, how should I put it, quantum in nature. This is related to a subject in physics called quantum mechanics, the discrete choppiness of the everyday world. Planck's constant is a tiny number, 6.63 times 10 to the minus 34. The units are a little bit weird. Joules times seconds. But 6.63 is a little bit boring sometimes. So sometimes we just round it off to, in our homeworks, I usually just use 7 times 10 to the minus 34, just because I don't want to get you all hung up on the 6.63. Actually, Planck's constant has many different decimal places. If any of you are fans of the show Stranger Things, one of the last episodes of the newest season, the whole plot hinged around this girl. They were trying to unlock a safe, and the safe, you had to know Planck's constant to 6 decimal places, and this like cool radio nerd chick knew Planck's constant to 6 decimal places. Planck's constant has a measured value much greater than that, of course. Let's see if we just type in, let's keep that up in case we need it. Planck's constant. Here's a value, 6.6260715 times 10 to the minus 34. It's actually been measured with a very high degree of precision. And one of the reasons why is Planck's constant plays a huge role in many different areas of physics. You can think of it as a tiny increment of something called spin. Spin is a property that subatomic particles like protons and neutrons and electrons have. I don't know how much more I want to get into it. Basically, anytime you're dealing with the world of tiny things, either atoms or light, Planck's constant tends to show up. Planck's constant is considered a symbol of quantum mechanics. Anytime you're dealing with the discrete, choppy nature of atoms, Planck's constant shows up. For now, just think of it as a number, and you can worry about what the physics means at a different time. Did that help answer your question, Megan? Okay, thumbs up. I like it. Perfectly silhouetted by the window there. You've already tried several sample problems in the homework today with this. Normally, I do sample problems anytime I introduce a formula. I'm still going to do some today, so let's just put them on pause for now. For a moment, I'd like to just kind of talk about the difference between light and photons. Photons are little packets of light. So normally, when you're looking at a beam of light in a window, like let's look at this just kind of crappy picture that I have here. If you're standing in a cathedral and there's sunlight coming in through a window, this sunlight could be considered a beam. That's how we would talk about it. And a beam of light is usually considered to be comprised of many individual rays. A ray is a technical term for a hyper-thin beam of light. But even one single ray of light will contain billions upon billions of individual photons. So at the tiniest level, there are beams or rays of light. And those are when we deal with the macroscopic world, when we have an actual seeable beam of light coming in. On the other hand, photons are basically tiny, we don't want to say particles because they have wave-like nature. So what we say is tiny packets of light. And that's at the microscopic level. So one simple analogy is to say atoms have the same relationship to matter that photons have to light. If it's natural for us to say that matter is comprised of individual units called atoms, which are too tiny to see, then light is comprised of individual photons, which are too low energy to see. The way we discuss light depends upon whether we're talking about a beam, a very large beam, or whether we're talking about a very tiny packet like a photon. And there's kind of different rules for discussing them. The formulas that I gave you just a moment ago, the 1, 2, 3 formulas, those are definitely appropriate for when you're trying to discuss a single photon of light. But I'd like to take a moment to focus on a beam of light and talk about how we discuss a large amount of light first. That's the next order of business here. I'm going to erase here. So let's imagine we take a brand new light bulb. Okay, so let's talk about a beam of light. And let's grab ourselves a brand new light bulb. Let's plug it in to a light socket. And on the microscopic level, individual photons are coming out. But at the macroscopic level, they manifest themselves as a bunch of rays of light, leaving in all directions. In fact, maybe a better way to draw this, because I'm kind of mixing my modes here. Let me draw that light bulb a little bit neater and cleaner. And let me represent rays coming out of the bulb in all directions. These rays contain energy, okay? But imagine if you tried to measure the energy that is streaming out of a light bulb. there's actually devices that are used to do such a thing. And one such device is known as an integrating sphere. Here's something you haven't heard about before. It's called an integrating sphere. You actually plug your light bulb in here, okay? You close this giant sphere, and your computer screen gives you a readout of the amount of energy coming out of it. But if you think about it, when you plug a brand new light bulb in, energy is constantly streaming out in all directions. And the energy keeps flowing out of the bulb as long as you have it on. So you might have to sit around for a long time to wait for all of the energy to come out of the light bulb and have it die. A more appropriate question to ask is how much energy is flowing out of the bulb in a day or in an hour or even in a second. And then you're dealing with a different quantity. Power, or the energy per unit time, is the flow of energy out of the bulb, or it's a flow of energy. In the same way that there's a difference between measuring a jug of water in liters and trying to think about the amount of water that streams past you in a river. It would be awkward or even nonsensical to say how many liters of water are in the river, because the river kind of has no beginning and no end. It's just water that's constantly flowing by. Okay, rivers really do have a beginning and an end, but they're not well defined because you have to go up to the top of a mountain and find some snow melt or something. Anyways, you get my point. If you're a dude standing at the edge of a river, the quantity of water is a little undefined because it's constantly flowing past you. Or you could talk about the amount of liters per second flowing by. That's the idea behind power. Now, power can be used for any kind of system that requires energy. A hair dryer might be 100 watts. A guitar amplifier might have a power requirement of 200 watts. When we talk about light, we use a slightly different term than power: luminosity, which is the same thing. Energy per unit time. So luminosity is the same thing as power, but we sometimes call luminosity the power of light. So for instance, here's an old Edison style incandescent bulb. I use these for my refrigerator and sometimes for lamps. 40 watts is telling us the luminosity of this bulb. The units of luminosity are the units of power. 1 watt is defined as 1 joule per second. And you should think of it as the energy flow in all directions. For instance, if my light bulb is 40 watts, that means if you add up the energy of all the rays of light coming out of it per second, or it's 40 joules every second flowing in all directions. Usually luminosity is fixed. It's a fixed property of a light source. For instance, the luminosity of a bulb, 40 watts, does not depend if you are close to or far away from the bulb. One of these little Christmas tree light bulbs up here, they might have a wattage of maybe 1 to 3 watts, I bet, for a typical Christmas light bulb. There's a little Christmas light inside there. That's what's going on. The sun has a fixed luminosity. The luminosity of the sun is 4 times 10 to the 26 watts. And that's a lot more light than you think it is. Let's look at a table of common energies. Do I have such a thing? You guys probably don't have a book here, but if you do have a book, on page 120, they show you a table of common energies, the number of joules and various things. One of them that sticks out to me is the annual energy consumption of the United States. So the annual energy consumption of the United States of America, since it's annual, since it's per year, you can think of that as a power. It's not all in the form of light, so I'll call it a power. The power consumption of the USA is 1 times 10 to the 20 joules per year. Now you guys will notice that's not in watts, that's in joules per year. To convert it to seconds, we could multiply it by the number of seconds in a year if we wanted to. You'd get 10 to the power of 27 watts. That's pretty wild. Yeah. Wait a second, hold on. Did I do that right? No, I screwed that up. I have to divide by 3 times 10 to the 7 seconds per year. Wow, I almost screwed that up. That's 10 to the 12 watts. So the energy consumption of the United States is 1 trillion watts. And that means that's how many joules we're using every second. Let's just get a picture here from the internet. United States at night. NASA has a beautiful little picture here. What? Oh, here we go. Come on. There we go. I love this picture. It's a satellite picture of the United States at night, perfectly illuminated here. This picture teaches you a lot. Imagine the entire energy consumption of the United States of America. Much of that is in lights, toasters, cars, the whole thing, you name it. Video games, cell phones, it's all part of our energy budget. This picture is also interesting because it shows you why Rhode Island is one of the least good places in the world to do astronomy. Look at the amount of light pollution you get in Rhode Island. It's comparable to the light pollution of New York City. Where I went to college out here in Tucson, they have some very dark skies, which are great places to do astronomy. It's also very dry there, so it doesn't rain a lot. And that's good because cloudy days spoil your ability to see stars. What if we could surround the sun with a gigantic integrating sphere and capture all of its energy? In other words, suppose we could create what science fiction authors called a Dyson sphere, and we could make a giant solar panel bag that would surround the sun, and we would capture all of its energy. I wonder how much energy that would be. Let's try a little sample problem. Let's imagine a Dyson sphere. That is, suppose I create a sphere that surrounds the sun. It's a giant solar panel bag that's going to capture all of the energy of the sun. And I know the luminosity of the sun. It's 4 times 10 to the 26 watts. The question I want to ask the class is, how much energy will the sun emit in 1 second? Anyone think they can tell me the answer to that question? The amount of energy the sun will emit in 1 second? Anyone want to try that with me? How do I figure that out?
Are we gonna use like, this is Jennifer, by the way. Are we
Oh,
gonna,
hi.
Hi, are we gonna fit like a previous equation that we worked with?
You don't, you could think of it that way, but you don't actually need the equation. The answer to this is a lot more simple.
Okay.
You just have to think about what the units of watts mean. It's all about this guy here. Can you guys see my mouse? Oh, no. Can I annotate in this thing? I can't annotate on my screen.
Would it just be the same because a watt is joule per second?
Okay, but be careful what you mean by same. Adrian. Adrian, how about you give me an answer?
4 times 10 to the 26th power.
I'm more interested in the units than the number. Well, I'm interested in both.
Because a watt is the joule per second, yes?
Yeah, but you didn't give me any units of that answer.
Oh.
Yes,
4
yes,
times
you are
10
correct. Huh?
4 times 10 to the 26th power joules per second.
False. Joules per second is a luminosity or a power. I'm asking you for an energy.
Oh, then joules.
All right, say the final answer in one shot for me.
4 times 10 to the 26th power joules.
Now we're talking to each other. You see, it's not just about the number. You're right. The 4 times 10 to the 26 watts means 4 times 10 to the 26 joules per second. But if I'm asking you in 1 second, you're multiplying this by a second. Do you see what I'm saying? I see what's going on here. Is that greater or less than the energy consumption of the United States in 1 year? Here's a follow-up question. How many years, well, not can I, the question is could I power the USA with that? Adrian, you seem to be the only one who understands me. I mean, hell, guys, a little dialogue helps here. Adrian, can you answer that question too?
I just divided them.
Yeah. Can you walk me through that?
So, it would be, yeah, 4 times 10 to the 26 joules divided by the consumption of the United States. So,
Wait, 1 times 10 to the 20, that's joules per year, right?
mm,
What's 4 divided by 1?
4,
What's 26 minus 20?
6
What are my units?
years.
What does that mean?
The sun can power the United States for 4 times 10 to the 6th power years. So,
What is 4 times 6 in plain English?
4 million.
Yeah.
nice.
And that's not the sun. You didn't say that right. That's 1 second of total sunlight. If I could capture all of the light coming from the sun for just 1 sloppy little second, I would power the United States of America for the next 4 million years. So why haven't I done that then? Why haven't we done that? Doesn't that sound like a good idea? I'll never have to pay Narragansett National Grid again if I could just get 1 second of sunlight, right? So why aren't we doing that then? Where's my Dyson sphere? What's the problem, Bob?
Is it not possible? Like, would it just light it on fire or something because the sun is so hot?
No, I mean, does the sun light the earth on fire?
No.
What? Why couldn't I just, what if I just make the sphere really far away? Like, what if I put it out here? I'll put it far enough away where it won't, the sun won't really light anything on, I mean,
How
if
would
there's
you
oxygen. Huh?
how would you distribute it then?
What do you mean by distribute it?
Like how would you distribute the power from the Dyson sphere evenly?
Well, you'd capture it on solar panels, and then, I don't know, you'd have a big wire, I guess, a wire that went from the Dyson sphere to Earth. Because the solar panels will turn it into electricity, right? So I don't know. Maybe you'd harvest it in Tesla batteries, and then you deliver it back down to Earth by shuttle. I don't know. A couple of different ideas. Well, I think the point I'm trying to make is, if I'm trying to make any point at all, we don't have that much material to cover the sun, right? Because we're just like a little tiny planet that's sort of far away, and we don't get to capture all of those photons. Most of the beams or rays of light are traveling in random directions so that aliens can see our sun as a little star in their sky at night, right? All of those are wasted photons. The only photons that we're going to get to capture are the ones that we can capture at our solar panel, our detector, 1 AU away. And that's a different kind of quantity. The luminosity of a bulb might be the light that it gives out in all directions, but the amount that you get to capture over here at your solar panel, that's known as the brightness, and it's a different quantity, and I need to teach you about it. So one thing we could say is, unless we have a Dyson sphere, we don't get to capture all those, I could say photons, but I'll say watts. We capture a quantity called brightness. And brightness is the luminosity that gets splashed over the area of your detector. Usually what happens is you imagine yourself having a beam of light, and the beam of light is getting splashed over a panel. I'll try to draw a 3D picture here as best I can. And this could be 1 square meter, which is actually pretty big, a 1 square meter panel. I can't even show you a square meter here. Actually, this dry erase board is very close to a square meter. It's actually a little bit bigger than a square meter. That's a square meter right there. But it's very close to the area of this board. So imagine that this dry erase board was that square meter right there. The brightness is the wattage of light that's being captured by this dry erase board. Usually what happens is you try to imagine your luminosity being splashed over a really big sphere, like you see here. So here, my 4 times 10 to the 26 watts is being captured at each distance by a bigger and bigger sphere. Because the radius of a sphere is because the surface area of a sphere is 4 pi r squared, we can kind of create this very important formula called the inverse square law. The inverse square law shows you the relationship between brightness and luminosity. Let's draw a picture of it. Introducing a very important formula in astronomy. The inverse square law. It has 2 different variations. One is brightness is the luminosity over 4 pi r squared. The other version of it is brightness is luminosity over 4 pi d squared. They actually sort of mean the same thing. What happens is you have an object that's emitting luminosity. It's going to be spread over some large sphere. The sphere can be thought of as having a radius r, or if you're the observer over here, you can think of yourself as a distance d away from the sphere. And then you've got 1 solar panel at the surface of the sphere. And you're asking about what's the brightness, what's the number of watts that are coming across 1 square meter panel. Let's try a little sample problem. Find the brightness of the sun at 1 astronomical unit away. In other words, let's imagine that you're an astronaut on a spacewalk. And let's just get a picture here. And let's imagine you're going to be holding up a solar panel. All right, so this guy isn't holding up a solar panel. He's holding a cap to something. But let's imagine that instead of this being a cap, imagine this is a solar panel. And he takes this solar panel, it's 1 square meter, and he points it up at the sun. I want to know the wattage he could receive at that solar panel if it was a perfectly efficient solar panel that could capture all of the sun's energy. Do you guys know how to do this problem? What should I do? Which variation do I want? Do I want the version 1 or the version 2?
Would you use the radius of Earth?
No.
Okay, so then it would be the second one, right?
Yeah, it's not the radius of Earth because Earth is not the light source. The sphere is centered on the sun. So let me try to help with this here because I can understand this is confusing your first time around. Remember, Megan, the sun is the light source, right? And the light is being splashed all over a sphere like so. The light's going up here and there and there and there. But we're interested in the amount of light that's going to make it to 1 square meter, 1 AU away, right? In other words, we're interested in the light that's going to make it to this square right here. The radius of Earth wouldn't make sense because the radius of the sphere is a 1 AU radius sphere. Do you see what I'm saying? In other words, yeah, you might want to use version 2 and think of the distance between you and the sun as being 1 AU. They're the same formula. We should probably convert that to meters. If 1 AU is 150 million kilometers, can you guys tell me how many meters that is? Or do I need to make you do dimensional analysis?
150 times 10 to the 9th power kilometers.
Cool. I was figuring someone could do that. Nice. What? Wait, you mean meters, right? I think you said kilometers.
I meant meters, yes.
Hold on, my light bulbs. There we go. That's what was up. I needed my party lights. What's the luminosity that we're going to use? Well, what luminosity? No? No one?
Would you use the luminosity of the sun?
Yes, of course.
4 times 10 to the 26 joules per second.
Or let's just call it for now watts, okay? But you're not wrong. You're right. All right. So the brightness is 4 times 10 to the 26 watts divided by 4 times pi times 150 billion meters squared. Let's go punch that in.
This might be a stupid question, but how did you get, I know we converted 1 AU to meters, but how did you get like to the 9th power? That's what I'm confused about.
Okay, sure. That's fine. So it's 150, hold on. I thought you guys might be so good as to do that in your head. I think Adrian was. He's got some chops. So Adrian did kilometers in the bottom, meters in top. 1,000 meters is 1 kilometer. That's 6 zeros, that's 3 zeros. 6 plus 3 gives you 9.
I get it now. Thank you.
Got it. Sometimes you do that so many times that you don't even need to like do the dimensional analysis anymore. You just know that you're going to add 3 zeros on. But Megan, if you didn't, then you asked an important question and you still are at the stage where you need to do this every time until you get good enough for that, okay? And that's fine. It's fine. That's why dimensional analysis is good. It will always help you get there. Okay, anyway, so someone got a brightness for me? 2 sig figs will suffice. Talk to me. You know, a question I need to ask this class at some point, it's kind of an important question that I've been wrestling with is, do you guys prefer the live lectures or are pre-recorded lectures better for you? Because the administration pushes us to do pre-recorded lectures, and I have the entire class pre-recorded from doing it with Summer 1. But I'm figuring that you guys would like the live ones, right? If you're feeling less engagey, we can also do the pre-recorded ones. It's up to you guys. You got to just.
The pre-recorded ones are nice, but like sometimes I have questions that like aren't answered.
Okay.
I don't know how though.
Yeah, I guess. No, that's. I mean, that's how I would think about it personally.
I can't pay attention at all to pre-recorded lectures.
Oh, really? It's just not. Yeah, it's not engaging the same way.
It's just really hard for me to focus.
I can see that. It's like watching a boring movie.
I'm just kind of like forced to engage here, so it's a little easier.
Well,
to
right.
focus.
So this is me forcing you to engage. What's the damned answer then, Adrian? What are you getting on your calculator? See, because what's irritating for me is if I'm doing the live lecture and no one talks to me, then I'm like, what the fuck? So what did you, or maybe it just takes you guys some time to punch it. What are you getting here? See, it's not as easy to punch this as you might think.
I have
I
an
was getting
All right, just shout it out, whoever it is, I don't care. Wait, I heard 2 people, now I hear no people.
I got 1,400.
What are the units? That's correct.
Great. Brightness watts.
Careful, there are units down here too.
Watts per meter?
So you might wonder why I do the parentheses. The reason I do parentheses is because the square is distributed not only to the number, but the square is also distributed to the units as well. So try one more time.
Squared.
Watts per meter squared. That's the units of brightness. This is a famous number in space physics and engineering. This is known as the solar irradiance. The solar irradiance is the maximum amount of luminosity you can get from the sun at a 1 square meter panel. By the way, this is from space. By the time you get down to the ground, the atmosphere absorbs and scatters so much of that light that underneath the atmosphere, you only get 400 watts per square meter. The atmosphere actually absorbs about 1,000 of those watts, or about 2/3 of it. Pretty incredible if you think about it. So if you're using a solar panel on your house, I don't know what the efficiency of a modern day solar panel is, but I think it's about 50%. Every square meter panel on your house, you can get about 200 watts from it, which is enough to power a hairdryer. And if you have a whole bunch of panels, you might even be able to power all the lights in your house or store it in a battery. So there's quite a bit of energy to be gotten from sunlight. Okay. That's an important application of the inverse square law. We're going to be doing a lot of this as we go forward. Compared to the sun, other objects like stars give a much, much smaller number of watts per meter squared. All right, let's change tactics for a second. I'm going to erase. Here I go. The inverse square law in both of its forms is extremely important in astronomy. Usually we use this to calculate the brightness of a star on our sky, and we use this to calculate the brightness at the surface of a star. So this is for the brightness of a star on the sky. This is for the brightness of the surface. I shouldn't say of, I should say at the surface of a star. Let's try one more application here. If I told you the radius of the sun was 700,000 kilometers, or 7 times 10 to the 8 meters, I could use this to find the brightness at the surface of the sun. The answer would be L over 4 pi times the radius of the sun squared, 4 times 10 to the 26 watts over 4 over pi over 7 times 10 to the 8, meters squared. Why don't you guys get that one for me?
I got 65 times 10 to the 6th.
Nice formatting. Very impressed. 65 million watts per meter squared. It's hard to impress upon you just how much light that is. A panel the size of this whiteboard would allow 65 million watts through it. That's probably enough sunlight to melt the hair off your face, okay? Or to melt the hair off your head. It's interesting that we have designed this spacecraft called the Parker Solar Probe. Earlier, I don't know if it was Olivia saying something about sunlight catching you on fire. The Parker Solar Probe is a probe that is basically flying through the outer atmosphere of the sun. And the atmosphere of the sun is very low in terms of particle density, so it won't really melt the probe because of conduction. But the radiation is certainly enough to melt it. That's why, let's see if we can see some visualizations here. I don't know if they have a model of this on Wikipedia or on the Parker Solar Probe website. Let's find out. Whoa, this picture looks dope. So here's the spacecraft itself. but it has to be protected by a large foil aluminum shield or some kind of a shield that's going to protect it from sunlight as it travels that close to the sun. It won't quite get 65 million watts per square meter because it's not at the surface. It's a little bit outside it, but it's going to get quite a bit. Where's the shield? I was hoping to see that. Look at this thing. It's insane. There it is launching. I think they explain it here. Here we go. The spacecraft systems are protected from extreme heat and radiation by a solar shield. Incident solar radiation at perihelion is 650 kilowatts per square meter. Basically, just a tenth of what we calculated because they're a little bit further away. Yeah. 500 times more intense than an Earth's orbit, the solar irradiance. The solar shield is hexagonal, and it's made of reinforced carbon-carbon composite. Wow. Look at this. If the shield were not between the spacecraft and the sun, the probe would become damaged and inoperative within tens of seconds. So 10-second exposure to that much radiation would be enough to just melt your spacecraft's instruments. Pretty wild. Okay, the next topic we're going to cover is the microscopic world of atoms and the type of light that they emit. I guess I've got a couple minutes before tea break here, so I'll just kind of take one more set of notes and then we'll pause there, okay? So the first note that I want to take is about where light is formed. All light is formed inside of atoms when electrons, well, I don't want to say jump. I want to say when they drop from high to low orbit emitting a single photon of unique wavelength, frequency, and energy. And we're going to study a particular transition. These photons are called an emission line. And this whole process here could be thought of the process known as emission. So what we're going to do is we're going to study an atom in which there are a number of different orbits, and we're going to watch an electron drop from one orbit to another orbit and emit a single photon called an emission line. And that'll take a couple of minutes because we're actually going to analyze the wavelength and the frequency and energy of a particular atom. So let's take tea break, and when we come back, we'll learn about how hydrogen emits a very unique photon of light, okay? So any questions before I pause here? All right. Hi, everyone, I'm back. There we are. Someone was taking a little nap zone, huh?
Yes, if you
Just catching a few Z's. I feel that. I would have done it too, but I was afraid I wouldn't get back up.
I'm here, but I'm gonna keep my, it's Jenna, but I'm gonna keep my video off because I have my son with me today.
Okay. Well, we don't mind seeing him either, but that's all right. I get it.
Okay, thank you.
As long as you're here and appreciating the lecture and talking to me from time to time.
Yes,
Okay.
by the way, I do appreciate the live lectures better than
Oh,
recorded.
okay. These are the kinds of feedbacks I need from y'all. I need to see if I can print today's lab because I have to use a different printer today. I didn't think about that till just now. We're not quite ready for lab yet, but just in anticipation of it, because I know it takes you guys sometimes a minute or two. Today's lab, which I have totally not set up, is on spectroscopy. I'm going to have to kind of rig it up pretty quickly here. And we're going to be looking at different elements in the periodic table and trying to see what types of light they emit. And I'm about to teach you how that works. The lab is the spectroscopy lab. This is it as a PDF. You just need this one piece of paper, but it would be helpful if you had colored pencils. I've got a nice set of colored pencils here. I've actually got a pretty epic set of colored pencils and markers. Look at this. Ooh. And I'm going to be using that to color them in live, but any kind of crayon or colored pens, whatever you got, pastels. If you don't, you might be able to do this on your computer. Let me see if I can print this. I don't have that printer, but I do have this one, so I'm print one. We'll see if.
Yeah, I have it where I can highlight certain areas of it.
You mean like on the computer screen?
Yeah.
That totally works, Andrew. A digital version. All we're really going to be doing is we're going to be making lines. Here. Emission line spectra. We're going to be looking at what's called emission line spectra. That's where you heat up elements. This is a pretty good example of exactly what we're going to be doing today. So you'll have the spectrogram, and then you'll take your colored pencils or your colored markers, and you're just going to make lines wherever you see them. At one point, we will look at a continuous spectrum, and you might have to shade in some blocks, but I'm sure you can figure out how to do that with your MS Paint tool or whatever. I think I have this as a doc version as well. Sounds like my printer is working, which is good. This printer's not as good as the old one, so it takes a little longer. But it is, I think, working. Oh, God. If it doesn't print, I'm going to have some real soul searching to do here. Oh, there we go. It's just really old and janky. All right, so let's learn about how elements produce these types of lines. So in other words, the moral of the story was use colored pencils or crayons, or use some kind of a paint or a Photoshop program on your computer and draw the lines in. Hopefully you guys will all be able to figure that out. Here we go. Sorry. Okay. I've got mine right here. When you take a spectrum, you break light apart into its component wavelengths. There are different things that you can take a spectrum with, class. You can take a spectrum with a prism, and I used to have a very jazzy demo that I would do in class with a prism, but it required me to have this very bright projector light, and I don't have a light of 400 watt intensity, so it doesn't work quite as good. You can also use these other things here. I want to show you something else. Hang on a sec while I find them on my cart of toys. Hold on, hold on. Damn it. Here they are. Sorry, they were buried. This is something called a diffraction grating. A diffraction grating has very thinly etched lines, sometimes less than a few micrometers apart. And the lines are spaced so thinly together, the little etchings are so thin together that when light strikes them, they will disperse and separate into a rainbow. I'm wondering if I could show you guys by holding it up to the camera. Here. I'm trying to figure out on the fly how to do this. So here's me shining a white light source at the camera. Let's see if I can put this at just the right angle as to what I need to do is create a rainbow, but then get the rainbow scattered into the camera, which should be possible to do. Oh, you can see it on my chin. The camera uses an LED light. Whoa, look at that diffraction grating. See if we can make it on the board here. The angle is it's very sensitive to the angle. Well, it's not working as well as I want. To set up these demonstrations, you kind of need a very dark room, and it's much too bright out for me to do that. Well, in any case, I was hoping I could scatter a rainbow in there to the, oh yeah, you can just about see one there. No. I got an idea. Let's try one more. One more demo here. Just for fun, just to goof off a little bit. It's kind of a mess in here, but let's see if I can take this camera. Oh yeah, there we go. Can you guys see how this diffraction grating separates that white light bulb into a sort of spectrum there of
Yeah,
colors?
that's cool.
That's cool, right? Yay, I did a demo. So astronomers actually use these diffraction gratings to separate starlight into its component wavelengths. Look at that. You can see red on one side, violet on the other. Notice you're getting your VIBGYOR spectrum right there. If I twist it this way, oh yeah, cool. All right. It took me a minute to figure out how to do this. I can even do it with sunlight too. But if I open up those blinds, I'm going to spend minutes messing around with them. All right, cool. So you guys saw that. So the only point I was trying to make is you can use these things that you've never heard about before called a diffraction grating. Have you ever looked at the back of a compact disc, a CD, and seen the rainbow? I think I have a CD here somewhere. Oh, look, it's the Sundays. Haven't thought about these guys in a while, since like the 90s. All right. And if you look at the back of a CD basically is a type of diffraction grating. So you can separate white light into its component colors just by bouncing it off of those little pitted mirrors. This basically acts exactly like a diffraction grating. So astronomers actually attach things like this to their telescopes, and they use it to separate starlight into its component spectrum. Sometimes you get different types of spectra in nature. And in the spectrum that you just saw was a rainbow spectrum called a continuous spectrum. But I'm about to tell you about a different type of spectrum that's called an emission line spectrum. And that's where you take a very pure element like hydrogen or helium or sodium, you heat it up, and instead of getting a pure rainbow, you get all these individual emission lines. And I'm going to talk to you about the production of this emission line right here. It's known as hydrogen alpha, and it's maybe one of the most famous photons in all of physics and astronomy. Let's teach you the story of how hydrogen alpha comes to be. It's known as the 3-to-2 transition of hydrogen. So introducing, is this my good marker? No, this is my good marker. Introducing the 3-to-2 transition of hydrogen. Do you guys remember what a hydrogen atom looks like? This is going to produce an emission line. The emission line has a famous name, hydrogen alpha, or H alpha. Okay, Adrian, tell us about a hydrogen atom. What's it look like?
Well, it has one proton.
Yep. And?
One electron.
Right. And if you would ask me where's the electron found normally, it's normally found in the atom about 0.05 nanometers from the proton. This is its default orbit. And this orbit is sometimes called the ground state. The ground state is the lowest energy closest to the proton orbit that the electron can have. We're going to label the orbits with something called a principal quantum number, which is a lot of technical gobbledygook to say orbit number. Orbit number 1, n equals 1, is the ground state. And the ground state is located 0.05 nanometers away from the proton. That's a short distance, but so what? We're talking about atoms. There's another unit that people use when dealing with the worlds of atoms. Nanometers are a billionth of a meter. Sometimes people like to use an old-fashioned unit called the angstrom, where 1 angstrom is 10 to the minus 10 meters. That's 1/10 billionth of a meter. Another conversion factor is an angstrom is a 10th of a nanometer. Sorry. Let me get this guy out of the way here. Just bear with me here. An angstrom is a 10th of a nanometer. Now, rather than talk about the distances that the electron has from the atom, or from the nucleus rather, it's more natural to talk about energies. We define the ground state as the lowest possible potential energy state that the electron can have. So we often say that it's at 0 joules or 0 electron volts. So the energy of the ground state, or E1, is defined as 0 electron volts, where you'll remember that 1 electron volt is 1.6 times 10 to the minus 19 joules. We don't like to work in joules when we deal with atoms because the energies are so bloody small. We like to work in electron volts. Now, the electron is not allowed to orbit any closer than this to the proton, but it can orbit at different distances if it wants to. There's a second orbit called the n equals 2 orbit. Sometimes it's known as the first excited state because you have to excite the electron to get it to orbit up there. And then there's the second excited state, which is the n equals 3 state. And there's another orbit called the n equals 4 state. There's an n equals 5 state. In fact, there's a whole bunch of different orbits that this electron can have. The number of orbits is not infinite in energy, but it is infinite in number. And that's going to sound kind of weird. I think I better show you a slide here showing you the energy levels of a hydrogen atom. The energy levels of hydrogen have been well mapped out and measured by physicists and chemists. And this is a diagram showing you the number of different orbits a hydrogen atom can have. So here, when the electron's here in the ground state, it's at 0 electron volts. It can't orbit anywhere in between level 1 and level 2. But if you excite it with exactly 10.2 electron volts, you can get the electron to jump up to orbit 2. If you go up by 12.1 eV, you can get to orbit 3. And there's an orbit 4, and there's an orbit 5, and an orbit 6. And as the orbits get higher and higher and higher, they get closer and closer together until they almost become continuous. But eventually, there's a maximum energy that the electron can have. If you give the electron 13.6 electron volts or more, then boop, you pop it right off of the atom and you ionize your atom. So this is the energy it takes to rip an electron off of hydrogen. At the beginning of our story today, we're going to focus on an electron which finds itself here in the n equals 3 state, and it's going to drop down after a certain, you know, the electrons orbit around for maybe 10 to the minus 8 seconds or so, which is a long time for an atom. And then they drop from orbit 3 to orbit 2, and they emit a photon whose energy is exactly equal to the drop, all right? So let's try to explain this in picture form. At the beginning of our tale, we are going to remove the electron from n equals 1, and we're going to find the electron up here in the n equals 3 state. The electron is going to drop or cascade to the n equals 2 state, and it's going to emit a photon of unique energy, unique wavelength, and unique frequency. One of the things you learned in your office hours today is if you specify any one of these properties, say if I specify the energy of the photon, then the frequency and the wavelength are uniquely determined. So one of the rules that we learn is this rule here. The change in energy when the electron drops, the energy lost will be emitted in the form of a photon. So that's the energy of your photon. And in the case of the 3 to 2 transition, guys, what's the energy that's going to be lost here? If I go from this orbit to that orbit, what will be the change in energy? Well,
Are we doing it from level 2 to 3? Is that what the question was?
3 to 2. Do you follow me?
Would it be 2.1?
Sorry?
Would it be 2.1 for the? I'm just guessing. I don't know.
No, you don't want to guess. The electron is going to start here, which is 2.1 up from ground, right? And it's going to drop to this orbit here, which is 10.2 from ground. I want to know the delta energy here, the change in energy. The change in energy is the energy of the third state minus the energy of the second state, right? Does that help or does that make things more confusing? E3 minus E2. Did I just lose you there, Olivia?
A little bit.
Would it be 1.9?
Yeah. Megan's got it here. Olivia, all I wanted you to do is take this and subtract that to get 1.9.
Okay, I think I was trying to do that, but I was just off with my math.
Yeah, you ended up getting 0.1, which gave me the willies. Megan, although it is 0.9, I need to get a little bit more precision for what I'm doing here today. So in our case, the change in energy from energy 3 to energy 2, it's actually 1.895 eV. In that cartoon picture you saw, they were only doing 2 sig figs, but I'm going to need 4 for what I'm about to do today, okay? Actually, hold on a second. Yeah, perfect. All right. Sorry, I just had to check myself before I wrecked myself. Here's the thing that I want to know. I want to know what is the wavelength of this photon. Do you guys know how to do that? Have you been trained sufficiently? Let's write it up again. The 3:2 transition of hydrogen will emit a photon whose energy is 1.895 eV. The question is, find the wavelength of this photon. How do I do that, class? You're supposed to know. Oops, sorry. How would I find the wavelength given the energy? You can't find a formula for that?
Would you use C equals wavelength times frequency or no?
Well, the problem with that formula, Megan, you're getting warmer, but the problem is that formula can give you the wavelength if you know the frequency, but you haven't been given the frequency. So that's not going to work.
So then it would be the third formula.
Exactly. And what's that one?
Energy equals Planck's constant times times speed of light over wavelength.
Wavelength. Okay, we should really solve for the wavelength, right? So what do I get there? Megan, you know what to do? Psst, psst, psst.
Would it be E over energy over Planck's constant and speed of light?
If you do that, you're putting these guys down there. Then you get energy is H times C, but then you end up with 1 over wavelength. I don't think that's what you want, right?
Flip it.
Then flip it, right. Instead, you flip the wavelength up here and the energy down there. So it's Planck's constant times the speed of light divided by the energy. What are our MKS units of energy? Will electron volts work? See,
No.
Huh?
No?
No, what units do I need here for energy?
Joules.
All right, so let's convert it. 1.895 electron volts. What's the conversion? I put it up on the board a moment ago.
Is it 1.6 times 10 to the negative 19 joules?
Beautiful.
Or one, yeah.
Thank you, Olivia. So why don't you punch that up for me then? I'm going to push this down here for a moment. Could you give me 4 sig figs? I'm going to need it.
Okay. I got 3.032 times 10 to the negative 19th.
Joules, right?
Yeah.
All right. All right, so now let's plug that in here. Today we're going to need to use a slightly more advanced version of Planck's constant. Because I'm trying to get more precision than usual, we're not going to use 7 times 10 to the minus 34. We don't have to go stranger things on this problem here, but we should at least get 3 sig figs. We don't need 6. 3 sig figs will do us. Why? Because this emission line is very special, and I want to get an answer to 3 significant figures. You'll understand why later. Okay, so we've got 6.63 times 10 to the negative 34 joules times seconds. Multiplied, believe it or not, the speed of light is actually good to 3 significant figures. It's 3.00 times 10 to the 8 meters per second. And the energy, I'm keeping a little extra, is 3.032 times 10 to the minus 19 joules. Punch them up. Where's that? Oh, the glare is coming from the lamp, I think.
Would it be 6.56 times 10 to the negative 7th meters?
Beautiful. That's great. Now, can you tell me how many nanometers that is? Here, Megan, watch these moves. Rather than do dimensional analysis, let's try something different. 65.6 times 10 to the minus what?
8?
Very
Minus
good.
6. Yeah, okay.
Or 656 times 10 to the minus 9 meters. Or 656 nanometers. Where is that on the visible continuous spectrum? What color would that be?
That would be green or yellow.
Fuck no. Green is 5 to 550. Yellow is like 570 to 590. We're 656.
Yeah, it'd be red. My bad.
Okay, fine. It's a very pure red right here. Sorry, those lines should be blue. That's 656 nanometers right there. It's a red photon, a very pure red, and it's known as hydrogen alpha. Now, let's add that to our notes here. It's a red line, and it goes by the name of hydrogen alpha. You might wonder why. You might wonder why this is such an important photon for astronomers. Let me explain why. Let's take a trip to outer space together. I don't know, let's go somewhere like the Rosette Nebula. Somewhere out in space is a beautiful cluster of newborn stars which emit quite a bit of radiation, not only in the visible regime, but also in the infrared and in the ultraviolet, which I'll talk about in a minute. And these stars are emitting tons of light, which is heating up this surrounding cloud. This cloud is mostly made of hydrogen gas. As this cloud absorbs photons from the stars, the electrons jump from a low orbit up to a higher orbit. Some of them hit the n=3 orbit, and then they all start to drop down to n=2, and they all emit this beautiful red color. The red color that you see here is all from hydrogen alpha. This isn't just red light. This is pure monochromatic red light at exactly one wavelength, 656 nanometers. In that sense, this is kind of like a laser nebula because it's emitting the purest of pure forms of red light. And we see these emission nebula all over space. They're extremely important. A quick check of emission nebula will reveal hundreds and hundreds of pictures of cool nebulae in space with beautiful red light coming from them. This red light is all hydrogen alpha. It's all heated up hydrogen gas that glows with the 3-to-2 transition. We can see hydrogen alpha over space. It's so important that you can get a hydrogen alpha filter for your telescope to just collect hydrogen alpha light. Ooh, here's a gourmet one. A Botter H alpha filter for my telescope. I actually convinced the department to buy this because I needed it. I needed that for educational purposes, okay? And with this hydrogen alpha filter, you can actually attach this to your telescope and take awesome pictures, like the cool pictures that you just saw. I'm only allowing in the hydrogen alpha light. It's so important. That was simply the 3-to-2 transition of hydrogen. But you can see that each individual energy corresponds to some wavelength. There are other transitions that the hydrogen atom can do as well, and I'd like to show some of those to you. Let's go back a couple here. This picture attempts to show us the different emission lines that hydrogen is capable of producing. Y'all just calculated what's called the 3-to-2 transition. When an electron drops from orbit 3 to orbit 2, it emits a photon of wavelength 656 nanometers, otherwise known as hydrogen alpha. Now there's another emission line that hydrogen produces. It's called hydrogen beta. It's the blue line at 486 nanometers. Class, can you look at the chart and tell me which transition is responsible for the 486 nanometer photon called hydrogen beta? Which transition is causing this blue line? So by analogy, hydrogen alpha is caused by the 3-to-2 transition. What transition causes hydrogen beta? I can't hear you. Whoever's, I don't know if you guys are speaking to me or someone else. Or you can't look at this chart and tell me which transition? That should be fucking easy.
Yeah, the 6th line from the left.
Right, but
Going from level 4 to level 2.
That's what I wanted to hear. The 4-to-2 transition. You're going from level 4 to level 2. Was that Adrienne that I was just talking to?
Yes.
Oh, I see. You're sorry, you were hidden down at the bottom there. Okay, cool. So Adrienne, since you had to school these folks here, what about, this is called hydrogen gamma at 434. What transition creates the hydrogen gamma photon?
level 5 to level 2.
Excellent. If an electron drops from 5 to level 2, it'll create hydrogen gamma. Hey, are you any good at mixing colors, like, you know, playing with crayons and stuff? What color do you think you'd get if you mixed these 3 lines together? Red, blue, and purple. What color would that produce?
If we're just talking colors, that would make a purple, but I feel like this is a trick question.
No, it's not. It's just that simple. Blue plus red gives you purple, right? And purple plus purple gives you more purple. Well, it just so happens, Adrian, hold on a second here. It just so happens that I have a tube of hydrogen gas here. This tube, although clear it may seem, is full of a low density hydrogen gas. And among my many other toys to play with today, oops. Oh, please tell me I didn't break that. Oh, no. I have a power supply here capable of heating up this hydrogen gas. What's going to happen is this power supply is going to send a current of electrons through this tube of hydrogen gas. I need a pump here. Plug it in over here. Sorry, I had a So here's the tube. I had to plug it in down there at the bottom. Let's flip it on. Ooh. The CCD isn't, yeah, let's get that. What do you think? Just what you predicted, right, Adrian? The CCD isn't showing this, but here in my room, it's very, very violet, okay? You can kind of see if I turn it sideways, you can sort of see the violet scattering here. It looks a little, the problem is CCD cameras, the chip that's making this video happen is called a CCD, and they are really, really shitty at purple light detection. So what happens is it ends up looking a little bluish, but it's actually a dark violet color.
Is that a black light?
It's different than a black light, although black lights are produced in the same way. So let me tell you about the black light thing, Megan. There are different ways that people produce the black lights. The similarity that you're seeing there is black lights are usually created with a fluorescent tube. So they're basically doing the same principle where there's a gas in there, right? Black light means technically ultraviolet light. And your eyes are not sensitive to ultraviolet light. There are cheese ball black lights, which are basically just purple lights that they pretend are black lights. Then there are real black lights that emit ultraviolet light, but they have a little emission in the violet end of the visible spectrum. And those are real black lights. But usually the way they produce them, Megan, is almost the same. For instance, you'll notice that ultraviolet is wavelengths of light that are shorter than 400 nanometers, right? And you'll notice that some of the transitions that hydrogen makes are actually at shorter wavelengths. For instance, if an electron were to drop from orbit 2 down to orbit 1, it will emit a photon at 122 nanometers, and that's actually shorter than the violet wavelengths. So hydrogen actually will produce some ultraviolet light. And in theory, you could make a black light from hydrogen, but there's so much visible light coming from up here that you'd be competing with these photons too. I do not believe they use hydrogen to make the black lights. In fact, this is kind of lame, but I don't know what gas they use. Sometimes they actually have to coat the bulb with a certain type of material that'll absorb other types of visible light. I really should know that, but I don't know what gas they use to create black lights. but the principle is similar. In fact, we probably should have a discussion about the entire electromagnetic spectrum. There are many other types of light that exist in nature. Slide 63 will demonstrate this. Sorry, there we go. Your eyeballs are sensitive to a pitifully narrow range of light that goes from 400 nanometers, which you call violet, up to 700 nanometers, which you call red. And although your brain is capable of discriminating these wavelengths, they operate in a very, very narrow band of what is known as the electromagnetic spectrum. The electromagnetic spectrum is the totality of all the different types of light that exist in nature. The only thing that makes one type of light different from another type of light is the wavelength, the distance from crest to crest of the wave. But that doesn't tell you the whole story, because these different zones of light, they behave very, very differently when they interact with matter in nature. In some ways, this is kind of like the periodic table of elements, but for photons instead of for atoms. And just think about what you know about the periodic table for a second. Hey, come back here. Let's think about the periodic table for a second. The only thing that makes one atom, like hydrogen, different from another atom like iron is just the number of protons in the nucleus. That's what we've learned thus far, correct? But if you think about it, the way that oxygen behaves is totally different than iron and totally different than zinc. And no one would say that mercury is the same thing as gold, or that tantalum is the same thing as calcium. But really, all that's changing is the number of protons in the atom. And yet, somehow by changing the number of protons, you totally change the way that atom behaves and is perceived. You know what I mean? The same thing can be said about light. All you do is you change the wavelength of light, but it doesn't just change the color. It can actually change the way that light interacts with matter and the way it behaves in a surprising way. This is such an important point that we must take this as a note. This is very important. So introducing what are known as the regimes of the electromagnetic spectrum. So first, let's talk about this. These are sometimes called, the word is regimes. Regime is like a zone or a territory or a domain. The regimes of the electromagnetic spectrum. And the visible regime is the one that you guys are the most familiar with. So let's make a big long line here, actually. So this is the visible right in the middle. We're going to do it in order of increasing wavelength. So we'll do Vib G your. I'm feeling a little lazy here, so. This is 700 nanometers. Violet is 400 nanometers, okay? Sorry, I moved it just a little bit far away here. Your eyeballs are sensitive to these rays of light. But if you go to longer wavelengths of light, you can enter what's called the infrared regime. Infrared starts around 1,000 nanometers or 1 micron and goes up to about a millimeter wavelength. After a millimeter, you start to enter what's called the radio regime. When you tune into radio waves in your car stereo, you're tuning into light, not sound. The sound is, the light is converted to sound afterwards. At the short end of the spectrum, we have ultraviolet or UV light. UV light ends at 10 nanometers. Then we have two more zones. We have the X-rays, which are very short wavelength and high energy. They end at 100th of a nanometer. And then you've got the really deadly gamma rays. Gamma rays are the really short wavelength, high energy light that comes from nuclear explosions and power plants. Gamma rays are what turn you into a Teenage Mutant Ninja Turtle. That rock of uranium that I showed you earlier, that emits gamma rays. Bad, bad craziness, okay? So in other words, when you're talking about a black light, usually the light will emit a spectrum of light that's partially in the ultraviolet and maybe will give off a little bit of visible light, so you'll see the purple end. But there's a difference between the crappy $10 fake black light that you buy at Spencer's and a good high quality black light, like the kind that a butcher might use to kill germs in a butcher shop. Or nowadays, people are trying to kill the coronavirus with black lights. I'm not sure if that actually works or not, but it might. Let's just type in black light into Google and see what we get. Some of them extend to different dimensions. So this is like the kind of black light you might get at Spencer's Gifts. I don't know if they're going to have technical information on it, but let's see if we can figure it out. This is probably fake. Notice they don't give you any spectral information. They tell you the wattage, but this is just a total piece of shit. Okay, this is, I mean, this might be cool if you're tripping or something, but it's not a good blacklight that can make things phosphorescent glow. Let's type in UV lamp, see what comes up. Oh, here's one of the kinds that people use to sterilize things at butcher shops. Or here's the handheld wand. A friend of mine works in the fashion industry, and when she does photo shoots, she has to use one of these UV wands. This might give you some better information about what the spectral benefits are. Do you say how this says UVC and UVA? That's telling you how deep into the ultraviolet they're going. So let's go to the Wikipedia page. I'm only mentioning this because it's kind of related a little bit to coronavirus, so it's kind of topical. Not all UV lights are the same. There's different, people break up even the ultraviolet zone to different zones. Let's see if we can find it here. Okay. So the ultraviolet that's close to visible light is ultraviolet A or UVA, and that's 315 to 400 nanometers. That's long wave, black light, not absorbed by the ozone layer. They call it sometimes soft UV. Then we have UVB from 280 to 315, medium wave absorbed by the ozone layer. And then this, UVC, 100 to 280, that's very short wavelength and it's germicidal, meaning those photons have enough energy to destroy and kill germs, such as coronavirus. So the idea is you wave the UVC light over the thing, you kill some germs. Now, I don't know just how much of their wattage is going into UVC versus UVA, but you get the sense of it all. By the way, remember that this is something important to remember. In this chart, wavelength goes up here, right? So this is increasing. But energy is inversely proportional to wavelength. So energy increases here towards the short wavelength side. Gamma rays have more energy than X-rays. X-rays have more energy than ultraviolet. Sometimes people call this the red end of the spectrum. Sometimes people call this the blue end of the spectrum because this is longer wavelength and that's shorter wavelength, okay? Now, atoms, when they emit emission lines, they not only emit emission lines in the visible spectrum, But elements like hydrogen and helium and neon, they can also emit emission lines in other parts. Usually the emission lines will be in the ultraviolet, the visible, and the infrared. They tend to not have many emission lines over here because these are very low energy and these are very high energy. The nuclei of atoms, when you have nuclear reactions, they emit X-rays and gamma rays. And radio waves tend to come from molecules, like the vibration of molecules. Different strokes for different types of matter. Do you guys have all that down? It's beautiful, but I need to erase it. It's important that you learn this if we're going to have an intelligent conversation about space. How am I doing on time here? Oh, not much time left. Okay. I need to tell you one more thing before we do our lab today. I need to tell you about the 3 different types of spectra that are produced in nature. Now, when light is emitted by different objects, the light can take one of 3 forms. You can sometimes get a continuous spectrum, sometimes you can get an emission line spectrum, and sometimes you can get an absorption line spectrum. All light, if you break it apart, falls into one of these 3 categories. This cartoon attempts to show you how you get the 3 different types of light. Rainbows are produced by things like light bulbs. Gases tend to produce emission lines, but if you shine white light through a gas, you can sometimes get an absorption line. The man who figured out how the 3 types of spectra are produced was a famous Prussian scientist by the name of Gustav Kirchhoff. Check out this very serious looking fellow here. He came up with what are known as Kirchhoff's 3 laws of radiation. And he was an expert in the subject of spectroscopy. Look at this guy. You don't want to mess with that dude, okay? Gustav Kirchhoff basically heated up elements with flames and Bunsen burners. And by studying when sometimes you'd get a rainbow and when you would get emission lines, he came up with what are called Kirchhoff's 3 laws of radiation. And they're sort of a classic in astronomy. They're the basis for spectroscopy, which is your lab today. Let's list them down. Kirchhoff's 3 laws of radiation. And this is going to give us good judgment about how the different types of spectra are produced in nature. The first law is called the law of black bodies. And black bodies is an old-fashioned term for things that glow because their temperature, like coals in a fire could be considered black bodies because when you heat them up, they glow. The law of black bodies states that a hot, dense solid produces a continuous spectrum. And you guys will remember that continuous spectrum is just a code word for rainbow. The meaning of the law of black bodies is this: hot, dense things glow with what you might call white light. They contain a complete rainbow, okay? And it does not depend on the element. Only temperature. The second law is the law of emission. This one does depend upon the element. And the law of emission is going to explain, let me just use my pictures to help my argument here today. Yeah. So we just talked about how we get a continuous spectrum like this one. Now I'm going to talk about how we get all these emission lines, okay? The law of emission states a hot, thin gas produces an emission line spectrum. And this does depend on element. Each element produces a unique emission line spectrum. As an example, the spectrum of hydrogen, which you will look at in your labs in just a minute, produces 3 emission lines, 1 red, hydrogen alpha, 1 blue, hydrogen beta, and 1 purple, hydrogen gamma. But that's just hydrogen gas. Forgot my N. That's red, blue, purple. Other atoms do not produce the same emission lines. So here's hydrogen. I should actually save this. This is pretty damn good. Save image as. I'm afraid I'll never find this again. Astro element. All right, we'll just save it in AstroPix for now. Here's hydrogen, red, blue, purple. Sodium produces a couple of yellows. Mercury produces other atoms, red, orange, yellow. No 2 elements are exactly the same. They sometimes call it the chemical fingerprint. It's possible to combine the first 2 laws to get a third law called the law of absorption. Whereas emission involves electrons dropping from high orbit to low orbit, you can also get electrons to absorb photons. And that produces our third law, the law of absorption. The law of absorption states a cold, thin gas in front of a black body, in front of a star, or in front of a light bulb produces an absorption line spectrum. Taken together, Kirchhoff's 3 laws of radiation are the basis for a sort of tool or an art form known as spectroscopy. Spectroscopy could be considered an art or a science. It's got elements of both. You know, it's science because you're measuring, but it's art because it takes skill to do it. It's the art or science of breaking apart light into spectra. A spectrum is where you separate it into its component wavelengths. That means component wavelengths. And analyzing the elements that produce the light. To do so, you could use a prism or a diffraction grating. Here's something called a spectroscope. They call it a spectrometer, but whatever. Scope means you're looking, meter means you're measuring. And you'll see that there's a diffraction grating in there. Can you see that? And usually what happens is you look through this thing. Can I do this? Can you guys see? Oh, I got an idea. Hold on, let me do something kind of cuckoo here. Here's a source of light. What type of spectrum do you think that would produce? Absorption, emission, or black body?
Emission?
I would have thought so too. Why did you say emission?
Because the butane, it's a hot, thin gas.
I believed the same thing as you before I tried it. Now let's see if you can actually see the spectrum of this, because this is how we're going to do our lab today. I'm going to hold the light up. You have to look kind of to the left. Oop, I almost had it there. What type of spectrum does it produce?
It produces the rainbow, a continuous spectrum.
Yeah. Can you, now this blew my mind the first time I saw it, because I was expecting emission, but instead I got continuous. Can you tell me why this is a continuous spectrum? So I would have thought the same thing. There's butane gas. You realize it's not the butane that's emitting light. It's the oxygen that's been heated up. Or it's a chemical reaction between the butane and the oxygen and the spark. Here's the thing. The gases that are in here that we're going to look at in spectroscopy, remember that thing? The gas inside that tube is at a very, very, very small fraction of the density of the air in this room. Kirchhoff said hot, dense, solid, but he really should have said hot, dense thingy. It turns out that air is so dense that if you heat up air, you do not get an emission line spectrum, you actually get a continuous spectrum. And that's why if you ever go look at a campfire, this is not an emission line spectrum here. This is actually a black body flame, because the glowing air is so dense that it actually glows just like a piece of metal. So that can be, you can know the laws, but you can sort of misapply them if you take the word. It's very tricky. You have to get experience and learn about things. And that's what you're going to do in your lab today. We're going to look at a number of different elements. We're going to heat them up. I should be able to show you emission line and continuous spectra. I'd like to show you an absorption line spectra, but the problem is you need a gas that's really thin and really cold. And the temperature, the room temperature that I'm at here is too warm to easily produce an absorption line spectrum. It turns out that the sun does produce an absorption line spectrum. I think it's going to be hard to do, but I'm going to try it today. Let's look at the spectrum of the sun taken by my old grad school alma mater, BU. They have a heliostat with a high resolution spectrograph attached to it. And when you take the image of the sun, at first it looks like a rainbow, but you quickly discover that there are thousands upon thousands of dark absorption lines in the spectra. The reason why there's so many is, although they only exist in trace elements, the atmosphere of the sun actually has all kinds of different elements in it. Calcium, nitrogen, iron, whatever, you name it, even titanium, it's in there. And all these different elements produce different absorption lines and are produced when white light from lower levels passes through the upper atmosphere of the sun. So this is an example of an absorption line spectra. Usually when you're dealing with a pure element, the absorption line spectra of hydrogen, for instance, would look just like its emission line spectrum, except in reverse. So here's a picture of hydrogen seen in emission. you can see the alpha, beta, gamma rays, or alpha, beta, gamma photons. And an absorption version of hydrogen would be white light with exactly those wavelengths removed from the spectrum. And that's because the electrons are absorbing photons and jumping from low orbit up to high orbit and removing them from the spectrum. Okay, we're going to do a short lab today. I think this is going to be as complicated as it is. I may need to delete some. My phone is almost out of memory, and I meant to delete pictures from it because I'm going to use my phone to look into the spectroscope, but I sometimes discovered that I need to take pictures just to kind of stabilize the image. And it just occurred to me that I might be almost out of space, so I'm going to delete some dumb photons of just me hanging out with my friends here. I'm just looking for photos I can kill. I do not need a picture of my omelet 2 days ago. That was not smart. Okay. So I got rid of a couple of photos here. Hopefully that'll be enough in a video. I did try to take a couple of photos of the comet, but they didn't all turn out so great. All right. That should be enough to get a few snaps. All right, everyone get your colored pencils ready, and we're going to do some spectroscopy. This is lab number 6 today, correct?
Yes.
All right, give me 1 sec. Let me get my stuff here. Actually, it works pretty good when I held up that webcam. So if the phone starts acting up, I might go with the webcam. We'll see here. This has more mobility. I need to activate my Wi-Fi. All right. All right, so I've got my spectrogram. I've got a spectrometer, which I'll use to analyze the light. The spectrometer has a diffraction grating. You can see it in there. It's going to, in fact, what happens is light comes in this tube. There's actually a really narrow slit that's cut into some photographic film. Can you, I don't know if we can see the slit in there. You can, oh, can you just see that little tiny slit there? Light's going to come into the slit to collimate it into a beam. It comes down here and it hits the diffraction grating, and then it disperses it onto a piece of film with the wavelengths printed on it. What's going to be irritating about this is, where's my pencil here? I need to get my elements and my power supplies here. So maybe I want to be able to see you guys at the same time. I think I'll just put it on this chair. Now I can heat up the elements here, and I can hold my spectroscope up to it. All right, that should work. So I'm kind of winging this here, guys. Bear with me. Let's see if I can connect to the iPhone. Share screen. iPhone. Sometimes you have to do the computer first. Sometimes you have to do the phone first. It's searching. Okay, let's try it a different way. Stop share. Let's share first. iPhone. Come on, baby. Pick up. I need this to work today. I need this to work. I guess I could try to just use the webcam. Would just be so nice. All right. It's being a jerk. One more time. Otherwise, I'm going to have to restart. Oh, there it is. Jesus. Just when I'm about to give up on it, it always works. Come on, baby. It says, it sees the Zoom. Now I'm just waiting for it to connect. Sorry about this. Okay, while that's, it lost it. I hit the wrong button. Fuck. I wish Zoom would figure this out. Okay, let's. Thing is, I can't. I'm a compulsive person, so I want to keep trying. I had it. I should have just left it alone. They said if I don't see it, I should restart my device. That's what I'll do. Meanwhile, let's use the camera here as best we can until I figure it out. All right, so can we see the paper? Let's get our name up here, okay? The section is AS1010 Summer 2. And this is Lab 6 spectroscopy. Going forward, this does not look very good. Having Lab 6 on here will be very helpful, okay? Let me try to turn this back on. The camera on the iPhone is a little nicer than this thing, so. All right, we're gonna have to study a couple of gas names. We won't have a ton of time, but let's put some ones we'd like to look at. Hydrogen. I believe I have neon, I have mercury. Let's see what else I've got here. I'm going to try to share this one more time. Yes. Yes, come on. You can do it. I'll just let that chill for a second. I have hydrogen. I have neon, helium, and mercury. Ah, there you go. There you go. Finally, guys, it's finally working. All right. I don't know if we're going to do all these. We'll try a few. So hydrogen, helium, mercury. I've wasted so much time just trying to get my phone working. Wow, it's freezing up there, huh? And neon. It'd be cool to do a incandescent bulb. That should give us a nice rainbow. And then the solar spectrum. I don't think we're going to do all these because I think we're going to run out of time. And this lab is notoriously fraught with technical difficulties, as you can tell. It's obviously way cooler to do this in person and look through the spectroscope yourself. But, you know, we can make do. This lab actually translates reasonably well. A couple of things I need you to notice. The units here. You'll notice that they have violet on the left and they have red on the right. But what you'll discover when you look through your spectroscope, let's see if I can zoom in a bit here. You guys can see that they put 700 on the left and they put 400 on the right. So what's happening basically is the spectroscope is reversed from this and they're using different units. Here, they're using 4,000 angstroms, and that corresponds to 400 nanometers on the spectroscope. So all we have to do to go from nanometers to angstroms is just add a 0. That shouldn't be too hard. The trick is to watch out for getting reversed here, okay? So without further ado, let's try to look at the hydrogen spectrum. Got my tube here, all right? I'm going to attempt to look through the spectroscope. The hydrogen gets quite a bit of contamination, so you're going to have to watch out for contamination here. Let's see. Will be helpful for me to stabilize this. Oh, fuck. There's a flash on it. Sorry. All right. I think I got it. Did you guys see that? Woo! Can you hear that? We'll just turn that little puppy off. Okay, guys. We're going to try to put lines where we see them. What would you say that red line's at there?
We're looking at the bottom portion, right? Like the,
Yeah.
not the 1.9.
The top is the energy in electron volts, but we want the wavelength in nanometers.
Okay. Like 650?
Yeah, I agree with that. Now I'm going to take out some fancy pens here, some fancy pencils. Hold on a second. Switchblades come in handy during your lab. All right, there we go. Crayon. Take out, I'm gonna need a violet. I'm gonna need a cyan. All right. So I took out some colored pencils. I have a red, a violet, and a cyan blue. Okay. And what I'm gonna do is, here we go. Take my red crayon. Here's hydrogen. So that's 600, 620, 640. We're going to make a red line right at 650. We know it's 656, but whatever. There's our hydrogen alpha line. Okay. Can you guys do that on your papers too? How about the hydrogen beta? What would you say? I think I might have a slightly better one here. No. Ooh, that one came out good. What would you say the wavelength of the hydrogen beta line is?
515, 520.
False. Look what's going on here, dude. 400 is here and 500 is here.
490.
Yeah, this is 450. These are 10. 460, 470, 480. That's 490. Maybe 485 or something. Let's say 480 rather than 490, okay? Oh, shoot. No, I hit stop share. No, 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 no. Okay. Oh, no, please work. Please work. Oh, I told myself I wouldn't do that. Oh, yes. Oh, thank God. I almost had a conniption there. All right. So now I'll grab my blue. Ooh, nice reflection. Okay. So let's see. It's all backwards here. So that's 42, 44, 46. That's 480 right there. That's what put our blue. That's hydrogen beta. And the hydrogen gamma, guys, do you see on my pictures, can you see all that stuff there? That's all background contamination. Hydrogen is so volatile that little bits of air comes in. That's the spectrum of air sneaking in there. It's now let's see if, I think one of these you could actually see the hydrogen gamma somewhat. You can just barely see hydrogen gamma. Can you guys see it there? Can you see my mouse on your screen?
Yes.
Do you see where the mouse is pointing to? It's quite faint and it's distorted, but I'm pretty sure that's the hydrogen gamma right there. You got to squint to believe me, but it's there. What would you say is the wavelength there? This is 400.
Maybe like 430.
Yeah, I'll go with that. So, 42, 44, 430 would be right in there. So there's your spectrum of hydrogen. You guys got that? Oop. Does anyone not have access to colored pencils and things? Has everyone figured this out? How many people are even listening to me right now?
I only have like a red and a blue, but I can make it work, I think.
Yeah, make it work. Some of them get more complicated, but red and blue are good to have. Those are probably the two most important colors. Be nice to have a green in there. All right, so you're gonna make it work somehow, right?
Yes.
All right, so what do you want to try next? Should we try helium? These are all, look at my fancy colored pencils here. I should probably take out a couple more while I got the chance. There's an indigo, green, yellow. Let's grab all these. kind of skimpy on the oranges, you know? I guess they got one orange. Oh, wow, those are nice. Those are really nice colored pencils. All right, let's close this up. Okay. Welcome to Brendan's home laboratory system, okay? I miss my lab tech every day. Helium. What did I do with that hydrogen tube case? I want to keep all this organized. Oh, here it is. Sorry, these things are expensive, and with this working from home thing, it's just not as easy as it looks, right? I mean, sometimes it is, but. There. Helium's here. Just bear with me here while I open this up. Ooh, what's the first thing you notice? This one glows kind of orangey, right? Can you see that the tube is not the same? Yes. Okay. So let's get our spectroscope. Oops. Those came out pretty good. Let's see. Any of those come out okay? Ooh, terrible. Oh, terrible. Oh, no. I thought, oh, yeah, here we go. Mamma mia. That's good. Okay, so, whoop. Let's get rid of you because you suck. Let's get rid of you. You suck. Let's get rid of you. You suck. But you are a keeper. I should have just gone with my first shot there. Okay, guys, play with me. What's the red? This is helium's red emission line. It's not the same as hydrogen alpha, is it? What's the wavelength?
$660.
I agree. So take red. 620, 640. There's 660. Notice it's not the same as hydrogen alpha. It's not even the 3-to-2 transition. It's some other transition. I forget what produces the, I'm actually kind of curious. If someone wants to look up on Wikipedia the spectrum of helium, you could tell me what transition that is. Okay, let's go back here. Hey, by the way, guys, what do you think about this line right here? What color would you say that is? Because boys and girls sometimes give me different results when I've noticed guys tend to think it's one color, girls tend to think it's another. What color do you think it is?
It looks like yellow, orange.
Yeah. Sometimes people say orange and sometimes people say yellow. Now, I have convinced myself that it was girls saying it was yellow and guys, I can't remember which it was. I just noticed that there was a small gender difference in people's interpretation. It's funny, people will get really adamant about it in the lab. I don't know how it's translating over the CCD. I guess it kind of democratizes it a bit. But when you look at it with your own eyes, I can go back and forth between yellow and orange. I don't know. I guess it's gold. Gold could be. I'm going to say yellow, but some people say orange. So you guys can choose whichever one your heart desires. Or maybe what we'll do is, in the spirit of fairness, we'll try to blend yellow and orange to make it a kind of golden color. Oh shoot, what was the wavelength though? What would you say roughly?
580.
Yeah, 580. So I'm gonna try to get both in there. So I'll go to 580. First I'll slap down, 580 is really in the transition boundary between orange and yellow. So first thing I'm gonna do is I'm gonna make a yellow line, okay? And then I'm gonna kind of sort of overgo it with some orange to give it a kind of golden color. I don't know if I succeeded or not. I'm being a little ridiculous here. I'm just trying to have some fun. Okay, looks like we got a couple of aquamarine or tealish kind of lines. What are the two teal lines at? One's at 500. What's this?
500, 490.
Yeah. I'll buy that. A little fun art time here. So I'll use this kind of, this isn't quite teal, but it's, you know, it's close. It's kind of fun to try to get the colors right. That's part of the fun here. I don't need you to go too crazy. If you can fake it till you make it with whatever you got laying around the house. I know you guys aren't necessarily stacked up. This color here, these are kind of indigo. It doesn't really start getting violet until you get closer to 400. This is a pair of indigo lines. That looks like, if that's 450, 440, and 470 maybe? I have a somewhat indigo color right here. It's, that's really deep indigo. Maybe I'll get fresh with this. So one was like 470. And I'll use an even darker indigo because I've got the fancy crayons to do it. And that was at 440. I'll save that for violet. So that's kind of what I have for the spectrum of helium. You guys follow me there? Trying to hold it steady, it's hard. Actually, maybe I can do that flippy thingy. That's a little nicer. Let's skip mercury for now. Let's go right to neon. Let's do one more emission line spectrum. Neon's kind of fun / not fun. These can get hot. Oh, that didn't sound good. Here, let me put this. Neon. Whoa. Look at that, huh? That's where we get the Michelob sign at a bar from. I wonder what we'll see here. Let me try to see. Well, I'm trying to take the photo at the same time. Got it. Sorry, that's, I'm holding the phone and snapping the picture and trying to tilt the spectroscope. It's not easy. That came out pretty decent. You can see there's actually quite a bit more in some of, did you see that one where you could see all the green lines? Neon actually has a bunch of green lines in it too. You could kind of see them flare up for a second. This is crap. That's gotta go. Can you guys see there's some faint green lines in there too? They're subtle. We're gonna go with this picture. This one came out the clearest, okay? So we got a lot of red lines here. Let's break it down. I count, this is 650, right? I count, there's actually 2 red lines over here that you can't see. 1, 2, 3 after 650. And I happen to know there's 2 over there, but we won't do that. All right, so 650, 1, 2, 3. Let's get your red line, get your neon out. Let's go sideways here. All right. Don't forget to go to neon. There's sort of 1, 2, 3 lines there. All right. We're going to kind of wing this one. How many red lines do we see? 600 is kind of orange. So I'd say 1, 2, 3, 4, 5, 6, 7. Let's just slap 7 lines in there. But don't go all the way to 600. Okay. I don't know why some are longer and some are shorter. It shouldn't be like that. Looks like we've got about 4 or 5 orange lines in there, right around 600.
Hey, Professor, I'm not sure if it's me, but are you working on 3 or 4?
I'm working on 4. I skipped mercury. You know what? I tried saying this, but I wasn't very clear about it. I think we're going to run out of time, and I think we can just put an X next to mercury, okay?
Okay.
Because I don't think we're going to have time to do that. I want to do the solar spectrum, and I want to do the incandescent spectrum. So let's just skip.
Okay.
Is that cool?
That's cool.
Yep. All right. I see 3 yellows. Yellow is very narrow range. That's, let's see. Sorry, 550, 560, 570, 2 at 580, and maybe 1 at 590. And that's it. That's all the lines we could see. Oops, sorry. That's all the sort of lines I could see for neon. Neon has crazy numbers of red lines. You know what? You couldn't see them there, but there's 2 fainter ones up here too, but my exposure was too short to capture those. All right, let's see if we can do the incandescent spectrum. I've got a very nice incandescent bulb here. Right. Okay. Incandescent has a filament. Do you know what kind of spectrum this is going to produce, students? Take a guess. What have we learned today? What kind of spectrum is this going to be? No one? What kind of spectrum am I going to get?
Continuous?
Very good. Let's try to get the colors right. Wait a sec. Hold on. Come on, baby. It's too bright. Wait. Let me go back here a bit. Oh, I almost have it. Fuck. All right. Sorry, that was hard. The thing is trying to focus, and it's so damn bright. Let's see if any of those look okay. That actually might be the best one to go with. So you can't see the violets very well. The CCDs have low sensitivity to violet. All right, let's start here. I would say that violet goes from 400, but by 450, it starts to get kind of indigo. So I want you to watch how I'm going to do this here. I'm going to get a violet. And the incandescent, we're going to start at 400. I also kind of know this from years. Whoa, is that really violet? Yeah, I guess. It's kind of a wacky purple, though. All right, I don't feel like looking any harder than this. So we're going to go purple starting at 400, and we're almost going to go to 450. Go up to 440. And the thing about a continuous spectrum is it's continuous. There's no lines. It's a smooth band, right? And then I'm going to switch over to a deep, deep indigo. Now, I actually have two different shades of indigo. So it all kind of looks the same on your camera there. That the CCD is, if you were sitting here, you would see that there were different colors there, but it's very subtle. Now I'm going to shift to a slightly different indigo. That's a deeper blue. And then if you notice, it kind of goes blue up to 500. 500 is the transition to green. So I'm going to go cyan here. And there's all these different shades of green in there too, but the CCD doesn't pick them all up. Let's see if we can see. It's kind of teal at 500. And it looks like it's green up to about that marker there. Let's see if we can see where that demarcation is in one of the other pictures. Oof, not very good. Oh, here we go. What would you say is the boundary between green and yellow?
Maybe 580.
Yeah, I'm actually going to dial it back to 575 just because I know I'm going to need some room there. You're not wrong. I'm going to need a little more room to go from. Yellow is a very narrow band. So let's do a, oh shit. Do I have a pencil sharpener in here? Guess this is. I could have sworn. I guess I can try my auto pencil sharpener, but it's gonna chew this thing up here. Wow, it works. So let's move you guys off to the side here. Let's do a nice big long band of green. There's different shades of green, but screw it. I'm not in the mood for that. And let's go up to about 575 or so. And then we'll do yellow. Yellow is really narrow. Oh gosh, you can't see anything there. Yellow is like 575 by 590, it's orange. So it's a super narrow range for yellow. All right, now it's time to get to orange. Orange is right at 600. And I think orange stops. This is mostly useless. That's useless. It's hard to see, but orange goes up to about 610, 620. Your eyeballs still will see 6 orange. You know, I can also show you that other screen with the visible continuous spectrum on it. That's cheating. We're supposed to be doing this in a laboratory, right? But I do have, hold on a sec. There we go. According to this, orange goes out to about 610, maybe even 620 or so. That's cheating, of course, but so let's go out, I don't know, let's go out to here. And then we transition to red all the way out. It's smooth, there are no breaks. Cool. Let's go sideways on that. Oops. You guys see that? Should we try to look at the solar spectrum? It's the last one, right? By the way, I have a really fancy version of this thing at home. For astronomy purposes, we have a very, very fancy spectrograph. It's extremely high resolution. This is what a professional grade spectrograph looks like. This one can produce really, really intense spectra. So you attach this part to your telescope right here. I was tempted to set it up for demonstration purposes, but right now it's the lens inside has been calibrated to my telescope. So although it would make a cool demo, it will give me tons and tons of work next time I take it to the telescope. So we're just going to try to use this bad boy. Now, I'm going to get rid of this here. I don't want to trip all over this stuff. Let's see if we can look outside the window. See how there's some blue sky up there? It turns out that if you want to observe the spectrum of the sun, okay, all you need to do is look at the blue sky, because the blue sky contains scattered photons from the sunlight, and the scattered photons preserve the spectrum of the sun. So believe it or not, just by taking a little patch of that blue sky there and focusing on it, we should be able to get a pretty good picture of this, or spectrum of the sun. Let's see how clear it comes out. I'm going to take a peek here. My microphone will be behind me, so I guess if you want, you can kind of watch what I'm doing here as I fiddle. So try to hold this up. That's bright as all hell. Ooh. Good. Bad. It's too much. I think the actual sun is drowning out. Let me try over here. That's a little better. Bear with me here. Now, all right. Just a moment. Class, it's kind of a shame, but what does the spectrum of the sun look like to you?
I guess kind of like the incandescent bulb.
Yeah, that's what it looks like at first blush. It's too bad because you can't really make them out, but oh yeah. Do you see, when I zoom in right there in that yellow line, can you see that dark band there? That's actually an absorption line. Now, part of the issue is a contrast issue. The white light is so bright that the lines are very faint. But when I look with my own eyeball through the spectroscope, I can actually see a bunch of dark lines all throughout here. This is really sad. This is one of the coolest things to look at as a student. But unfortunately, it's very, very difficult for me to get those absorption lines. You can actually see a couple of them in there. You can kind of see one there. You can kind of see one there. There's a few scattered all throughout there. Actually, a high resolution spectrograph will show lines all throughout this bad boy. It's easy to see with your naked eye, but it can be hard to see. Can you guys see there? It's slightly darker. It's very subtle. You can see one in the red there. Okay, so here's what we're going to do. We're going to recopy the incandescent spectrum, and we're going to do it fast, okay? So let's do red. Hold on, I need to steady this so I can have both my hands. I'm going to try to do this quick. So follow me and see, or you can copy and paste if you're using a computer or whatever. So there's the red. Orange is 600 to 620. I'll put a little spot of yellow there. I'm doing this quick and dirty, okay? It is essentially the same as the incandescent with some slight differences. And that's mostly the lines. So let's do some green. Some blue. Indigo. Dark indigo. Oh, I do have a violet. I have a bitter violet. And here's a real downright violet. I should have used this before. And what we'll do is we'll just take a number 2 pencil, a Dixon Ticonderoga, if that's what this is. Yeah, it's a black Dixon Ticonderoga. And we're going to make some absorption lines in here. I could clearly see one in the blue. There's a couple of random ones in the green. And there's one in the boundary between orange and yellow. We're kind of winging it. If this was a more advanced course, I would be very obsessed with you getting the exact wavelength of each absorption line. But here we're just kind of getting the flavor of the feeling, okay? And that's it. There's your spectroscopy lab right there.
Professor Janet, I have a question.
Yeah.
So I missed the homework. Should I refer to last summer's video, or are you going to post this one?
Can I, once I stop sharing my iPhone, it's gone. So before I answer that question, is everyone done with this here? Okay.
And this, can I have a couple minutes?
You need
I'm
a
just
couple of
copying
seconds?
down the absorption lines and that's it.
That's fine. So let me, if you're doing that, let me put that right there. And then I'll just talk to Janelle, okay? I got that right, didn't I, Janelle?
Close, Janabelle.
Janabelle, I'm sorry.
It's okay.
I don't, you're hidden for me right now, so it's always helps to have the name. With
I know.
Okay, that's fine. Okay. So Janabelle, they're exactly the same.
Okay.
And in that case, you know, it's nice to wait for your class because you're familiar with everyone here. But on the other hand, if you want to get it done, go ahead and watch the Summer 1 version, because remember, it takes an hour to render this video and another hour to upload it. And sometimes I forget that day. So why don't you go ahead and just use the Summer 1? You think you can find the Summer 1 video?
Is there any way you can send me the link? Or can I just go and click on the link you sent to us before and then navigate your channel through there?
Yeah, but I should be able to help you. Let me see if I can find that and put it in the chat, because I want to make sure you don't get the wrong one, you know?
Okay.
It should, I'm trying to stay consistent between the 2 semesters in terms of naming and what I do each day. It hasn't been perfect, but it's close. So I'm at my, hold on, I have so many tabs open. Just let me get rid of a couple of tabs here because it's stressing the system out. It's a tabby kind of day. Just a moment. All right. By the way, whoever was still working on the absorption lines, let me know when you're done, okay?
I'm all done.
Oh, okay. So let me stop sharing then. Hold on. This will make this a lot easier. Okay. Let's see. Today was homework 5, correct, students?
Is that it's a good idea to cycle on the subject.
Sorry. I was watching.
Go around it.
No, thanks. I was watching somebody else's YouTube to see what their lectures were like. Okay. Let's see. Summer 1, homework 5. This should be it. This is what we did today, isn't it? Honestly, I could have just showed this to you guys, but we're doing some live stuff with your class. Hold on. Let's just make sure that we see one of the same problems before here's the link. Copy. Let me chat it to you while that's loading. Janabelle in the chat log. Where's my chat log? Oh. Paste. Oh. Yeah. That looks exactly like it. And I should have done the exact same things in that class that I did in this one. Let's just. So Janabelle, you can just get busy and watch that one, okay?
Yeah, I'm gonna go ahead and do that right now. Thank you.
You got it. All right, so the rest of y'all, how you doing out there? You got your lab done? You got your homework done? Looking good, feeling good? Okay. So I'll stop the recording in a second. Give me some time. I'll try to get an estimate of your grade and see what those grades are in the exams, okay? I'm sure you're curious. Maybe Sunday I'll deal with that. Anything else that you guys need from me before I end?
No,
Okay.
thank you.
Thank you so much.
Yeah, you're welcome. Okay, guys, I'll see you on Monday then, right? 10 a.m. More homework Monday. All right, we'll get through this.
Thank
So
you.
I'll see you guys later, and I will eventually get this posted to the YouTube. Just give me some time, okay?
Okay,
All
thank
right.
you.